Hello there and welcome to Cosmos for Sleep. Tonight, we're drifting into the profound mysteries of wormholes. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe, let your eyes grow heavy, and let's begin. Wormholes are theoretical tunnels through space-time, offering shortcuts across vast cosmic distances. They are often imagined as bridges connecting two distinct points in the universe. The scientific term for a wormhole is an Einstein-Rosen bridge. This concept was first proposed in 1935 by Albert Einstein and Nathan Rosen. Wormholes are a direct consequence of Einstein's profound theory of general relativity. This intricate concept allows for space-time to be subtly folded, bringing distant points together in a way that defies conventional travel. While they are a fascinating theoretical construct, it is important to remember that they are purely hypothetical. No observational evidence for their existence has ever been found in the cosmos. These elegant cosmic pathways, known as wormholes, are theoretical tunnels through the very fabric of space-time itself, designed to offer serene shortcuts across the otherwise immeasurable and vast cosmic distances. Imagine the universe not as an empty void, but as an intricately woven tapestry, a four-dimensional expanse where space and time are intrinsically linked. Within this grand design, a wormhole proposes a gentle folding, a subtle pleat in this cosmic cloth, allowing for a journey that would otherwise take eons to be accomplished in a much more abbreviated time frame. This concept allows us to ponder how the universe might offer routes that bypass the conventional, lengthy trajectories, creating a sense of intimate connection between far-flung celestial realms. Such pathways hold the allure of swift passage, transforming daunting interstellar voyages into journeys of relative ease, at least in theory. They invite us to contemplate a universe where the immense scale is not an insurmountable barrier, but a canvas for ingenious gravitational designs. The very notion of bending the rules of cosmic travel brings a quiet sense of wonder, envisioning a placid transit through the universe's most profound structures. These remarkable theoretical structures are often envisioned as tranquil bridges, gracefully connecting two distinct points within the expansive universe, much like a placid river creating a direct route between two distant shores. Picture a smooth, ethereal opening, leading into a serene, winding tunnel, and emerging into another realm entirely separate from its starting point. This imagery suggests a cosmic subway system where entrances and exits are strategically placed, allowing a gentle transit from one galactic neighborhood to another. The idea is to circumvent the long, arduous path of traversing billions of light years in conventional space, opting instead for a direct, albeit theoretical, link. These cosmic conduits would not simply move an object through existing space, but rather would fold space itself, creating a direct connection that drastically reduces the effective distance. It's a vision of cosmic elegance, where the immense stretches between stellar systems could be traversed with a newfound grace, linking disparate regions of the celestial tapestry into a cohesive, interconnected network. The gentle curves of such a bridge would offer a serene passage, a tranquil journey across the universe's grand design. The formal scientific designation for these profound cosmic shortcuts is an Einstein-Rosen bridge. This name itself carries the weight of its origins, hinting at the intellectual giants who first conceived of such a concept. The term bridge is particularly evocative, as it perfectly describes the theoretical function of these structures: to span or connect two otherwise separate regions of space-time. It suggests a delicate architectural marvel woven from gravity and geometry, designed to gracefully link cosmic locations. This scientific nomenclature underscores the deep connection to the fundamental principles of physics, rather than merely being a fanciful notion. It grounds the idea in the rigorous framework of theoretical science, inviting a closer examination of its mathematical underpinnings and the subtle ways in which space-time might be manipulated. The name itself invokes a sense of a carefully constructed pathway, a deliberate connection within the vast and silent cosmos, offering a serene passage across cosmic divides. This groundbreaking concept was first meticulously explored and proposed in the year 1935 by two brilliant minds: Albert Einstein, whose revolutionary theories reshaped our understanding of the universe, and his colleague Rosen. Their collaborative work, published in a scientific paper, laid the initial theoretical groundwork for what we now refer to as wormholes. It was a moment of profound intellectual discovery as they delved into the complex equations of general relativity, unearthing solutions that suggested such peculiar connections within the fabric of spacetime. Their initial models, while not immediately practical for travel, ignited a spark of curiosity that continues to resonate through the scientific community. This historical moment marks the quiet birth of an idea that would profoundly influence theoretical physics and cosmic exploration, offering a serene glimpse into the potential intricacies of spacetime itself, a testament to the power of human intellect to unravel cosmic enigmas. Indeed, the very existence of wormholes as a theoretical possibility arises as a direct and elegant consequence of Albert Einstein's monumental theory of general relativity. This profound theory, which describes gravity not as a force, but as the curvature of spacetime caused by mass and energy, provides the fertile ground for such exotic phenomena. Within the intricate mathematical framework of general relativity, spacetime is not a static background, but a dynamic, malleable entity that can be warped, bent, and even folded. Wormholes represent one of the more extreme and intriguing solutions to Einstein's field equations, suggesting that the universe's geometry can be far more complex and interconnected than our everyday perceptions might suggest. It is within this serene and elegant theory of gravity that the concept of a wormhole finds its deep theoretical roots, emerging as a potential, albeit challenging, feature of the cosmic architecture. This connection to a cornerstone of modern physics lends wormholes their significant scientific weight, inviting continuous, thoughtful exploration into the universe's underlying structure. The core of the wormhole concept lies in its remarkable ability to allow for space-time to be subtly folded, thereby gently bringing distant points together in an almost imperceptible manner. Imagine taking a sheet of paper, marking 2 points far apart, and then folding the paper until those 2 points touch. A wormhole, in this serene analogy, would be the theoretical puncture that connects these two touching points, creating a direct passage that bypasses the long journey across the paper's surface. This elegant folding mechanism is what offers the potential for true cosmic shortcuts, dramatically reducing the travel time between celestial bodies that are otherwise separated by light years of conventional space. It's a profound reimagining of distance itself, suggesting that the vastness of the cosmos might be navigable through clever manipulation of its fundamental fabric. This conceptual folding of reality offers a tranquil vision of interstellar travel, where the immense gulfs of space are made traversable through the gentle curvature of space-time, a testament to the universe's subtle flexibility. Despite their deep theoretical grounding within general relativity and their captivating allure for cosmic exploration, it is crucial to reiterate that wormholes remain. Scientists, with their keen instruments and patient observations, have diligently searched the celestial tapestry for any subtle hints or gravitational signatures that might betray the presence of these elusive tunnels. Yet, thus far, the universe has held its secrets close. There are no confirmed sightings, no discernible distortions in light, nor any other direct or indirect indicators that confirm their physical reality. They exist for now as elegant mathematical solutions and captivating possibilities within the realm of theoretical physics, inspiring continued research and imaginative thought. The absence of evidence does not entirely negate their potential, but it firmly places them in the category of fascinating speculation, a testament to the boundless mysteries that still reside within the quiet expanse of space. The universe, in its vast and tranquil silence, continues to guard its deepest secrets, allowing us to ponder these theoretical wonders without concrete proof. This enduring hypothetical status reminds us of the delicate balance between mathematical elegance and observable reality. The serene quest for understanding continues, even for phenomena that remain beyond our current grasp, inviting us to dream of what might one day be discovered in the cosmic depths. The theoretical framework offers a soothing promise of future revelation, even as the present remains veiled in mystery. Their unconfirmed nature allows for a boundless expanse of calm contemplation. The original Einstein-Rosen bridge, though a brilliant mathematical construct, was inherently non-traversable. Its delicate throat would snap shut faster than light could possibly cross its threshold. This early model, while elegant, presented a significant challenge for any practical application, as it implied an instantaneous collapse. It meant that even if such a bridge were to momentarily form, any object or light attempting to pass through it would be immediately caught and crushed, making any journey utterly impossible. The concept, as initially formulated, served more as a theoretical curiosity, a peculiar solution to the equations of gravity rather than a viable pathway for cosmic travel. It highlighted the intricate and often counterintuitive nature of spacetime at extreme conditions, suggesting that not all mathematical possibilities translate directly into physically accessible realities. This early understanding of their ephemeral nature set the stage for further theoretical developments, seeking ways to stabilize these fleeting cosmic connections. The initial vision of an Einstein-Rosen bridge was one of profound mathematical beauty, yet also of an almost imperceptible fragility, a fleeting connection that would dissolve into the cosmic background before any conscious entity could even begin to perceive its transient existence. It was a silent, graceful acknowledgement of the universe's stern laws, a delicate whisper of possibility quickly hushed by the demands of physics. The non-traversable nature of this early wormhole model underscored the immense challenges in transforming abstract mathematical solutions into tangible cosmic pathways, reminding us of the subtle complexities inherent in the very fabric of reality itself. This initial representation was essentially a mathematical artifact, a peculiar outcome derived from the study of black hole solutions within general relativity. It emerged not as a deliberate design for interstellar travel, but as an unexpected byproduct of exploring the geometry around intensely massive objects. The equations that describe a black hole, when viewed from a certain mathematical perspective, hinted at a connection to another region of spacetime. However, this connection was purely formal, a theoretical link that did not imply a physical tunnel through which matter could safely pass. It was a serene revelation, a subtle whisper from the universe's deepest mathematical structures, suggesting hidden symmetries and unexpected relationships within the cosmic tapestry. The artifact was a testament to the power of pure mathematics to unveil potential realities, even those that seem to defy our intuitive understanding of space and time. It was a quiet, elegant demonstration of how the universe's laws, when deeply explored, can reveal surprising and complex geometries, enriching our understanding of the cosmic dance of gravity and matter. This mathematical elegance, while abstract, offers a placid invitation to ponder the universe's hidden dimensions and connections. The original Einstein-Rosen bridge also conceptually connected a black hole to a white hole, another theoretical region of space-time that, in stark contrast to a black hole, would repel matter and energy rather than attracting it. While a black hole draws everything inward, a white hole would, in theory, eject everything outward, preventing anything from entering. This pairing presented a cosmic paradox, with a one-way entrance on one side and a one-way exit on the other, making a coherent passage through the bridge impossible. White holes themselves are also purely hypothetical entities, with no observational evidence to support their existence. They represent a fascinating, albeit unconfirmed, mirror image to the gravitational pull of black holes, adding another layer of theoretical intrigue to the universe's extreme gravitational phenomena. The tranquil thought of such a cosmic repulsion allows for a deeper appreciation of the more familiar attractors in space. This conceptual linkage to a white hole emphasized the non-traversable nature of the early wormhole models, further underscoring the immense theoretical hurdles that needed to be overcome for any practical application of these space-time shortcuts. The elegant dance between attraction and repulsion, even in theory, paints a vivid and calm picture of cosmic forces at play. The Schwarzschild wormhole, a particular solution derived from the mathematics describing a non-rotating black hole, serves as a prime example of such a non-traversable wormhole. This specific type of Einstein-Rosen bridge would, in theory, connect two separate regions of space-time, but its nature would prevent any form of safe passage. Its defining characteristic is that its throat, the narrowest point of the theoretical tunnel, would instantaneously pinch off before anything, even light, could traverse its length. This rapid closure means that any attempt to enter would be met with an immediate and inescapable collapse, sealing the pathway forever. It's a subtle reminder that not all theoretical possibilities within the grand framework of general relativity are hospitable or even accessible. The Schwarzschild wormhole thus exists as a profound mathematical curiosity, a serene and elegant demonstration of space-time's complex geometry under extreme gravitational conditions, rather than a practical route for cosmic voyagers. Its ephemeral nature quietly speaks to the universe's intricate design, where even the most alluring shortcuts can be fleeting and unattainable. This specific model highlights the delicate balance of forces required for any sustained cosmic passage. The inherent instability of these early models meant that their delicate throat would indeed pinch off at an incredibly swift pace, far faster than any object or light could possibly pass through it. This instantaneous collapse rendered them completely useless for any form of interstellar transit. Imagine a bridge that forms and then immediately vanishes the moment you step onto it. Such was the fate of anything attempting to cross an unstabilized Einstein-Rosen bridge. The mathematical solutions that described these wormholes showed that the gravitational forces at play would cause the throat to constrict and disappear with the speed of light, leaving no window for passage. This intrinsic fragility underscores the profound challenges faced by physicists in transforming these theoretical curiosities into potential realities. It is a quiet testament to the universe's fundamental laws, which, in their serene elegance, often prevent such convenient shortcuts from materializing in a stable form. The swift, inevitable closure of these early wormholes paints a gentle picture of cosmic limitations, guiding our understanding toward the intricate requirements for any viable space-time conduit. Indeed, not traversable. Its delicate throat would snap shut with an ephemeral swiftness, far swifter than any particle of light could hope to traverse its fleeting pathway. This inherent instability meant that any object, no matter how minute or swift, would find its journey abruptly halted, rendered impossible by the immediate collapse of the cosmic passageway. It was a theoretical glimpse into a cosmic shortcut that, by its very nature, denied access, remaining forever out of reach for even the swiftest of travelers. The profound implications of this rapid closure highlighted the immense challenges in conceptualizing a stable, open pathway through the universe's most extreme geometries. This early model served to deepen the mystery rather than immediately provide a solution for cosmic navigation, offering a serene contemplation of physics' subtle boundaries. This initial theoretical construct represented more of a profound mathematical connection between two regions of space-time rather than a tangible physical tunnel designed for transit. It was an elegant solution derived from equations, hinting at a hidden relationship within the universe's fabric, but not manifesting as a concrete pathway. The Einstein-Rosen bridge, in its nascent form, was a conceptual link, a theoretical thread tying together distant cosmic locations in an abstract sense. It allowed physicists to explore the intricate geometry of the cosmos, revealing how space-time might be intricately folded, even if those folds were not immediately accessible. This distinction between mathematical possibility and physical reality is a delicate one, inviting contemplation into the deeper symmetries of the universe that may exist only in the realm of pure theory. It was a testament to the power of mathematical exploration, unveiling potential cosmic architectures that, while beautiful, remained beyond the grasp of physical interaction. The bridge, therefore, was a silent, intellectual marvel, a placid whisper of connection across the cosmic expanse. Indeed, this early model was essentially a mathematical artifact of black hole solutions, emerging as an intriguing byproduct of studying the gravitational properties of these intensely dense celestial objects. It was not conceived as a separate entity, but rather arose from the profound calculations that describe the spacetime surrounding a non-rotating black hole. As scientists, they found that these solutions naturally suggested a link, a theoretical bridge that extended beyond the familiar event horizon. This unexpected discovery underscored the deep and often surprising interconnections within the universe's fundamental laws, revealing how the extreme curvature of spacetime around a black hole could, in theory, hint at pathways to other regions. It was a serene and elegant demonstration of how pure mathematics can uncover subtle, unforeseen structures in the cosmic architecture, even if those structures are not directly observable or traversable in a practical sense. The artifact offered a quiet invitation to ponder the hidden dimensions of reality. Further elaborating on its theoretical structure, the original Einstein-Rosen bridge, a remarkable and equally theoretical region of spacetime that would, in principle, repel matter and energy rather than drawing it inward. Unlike a black hole, which is characterized by its inescapable gravitational pull, a white hole is imagined as a region from which matter and light can only emerge, never enter. This peculiar pairing created an inherent one-way street scenario. Matter could fall into the black hole side, but it would be forcibly ejected from the white hole side, making a continuous passage through the bridge utterly impossible. The concept of a white hole, with its outward pushing force, stands as a fascinating, albeit unconfirmed counterbalance to the immense gravitational attraction of a black hole, adding another layer of intricate theoretical possibility to the universe's extreme gravitational phenomena. This theoretical connection paints a serene picture of cosmic opposites, a delicate balance between drawing in and pushing away. It is important to emphasize, with a calm and measured tone, that white holes are also entirely hypothetical and have never been observed in the vast expanse of the cosmos. Just like their wormhole counterparts, white holes exist purely within the realm of mathematical solutions to Einstein's equations, with no empirical evidence to support their physical reality. They remain a captivating thought experiment, a theoretical mirror to the black hole, inviting physicists to explore the full range of possibilities within general relativity. Their unconfirmed status underscores the profound mysteries that still pervade our understanding of the universe's most extreme gravitational environments. The elegant symmetry they offer in theory is a placid reminder that the cosmos holds many secrets, patiently waiting for the moment when our observational capabilities can match the boundless reach of our scientific imagination. These theoretical entities serve as quiet beacons for future exploration, guiding our curiosity into the unseen depths of spacetime. The Schwarzschild wormhole, specifically derived from the elegant mathematical description of a non-rotating black hole, stands as a quintessential example of a non-traversable wormhole. This particular solution, named after the pioneering physicist Carl Schwarzschild, represents the simplest form of a black hole and, by extension, the most basic form of an Einstein-Rosen bridge. Its significance lies in demonstrating that even in the most fundamental black hole model, the theoretical connection it proposes is not a pathway that can be traversed. It serves as a clear illustration of the early limitations inherent in these cosmic shortcuts, showcasing how the universe's gravitational laws, as described by general relativity, could create connections that are mathematically present but physically inaccessible. This specific example helps to anchor the abstract concept of non-traversable wormholes in a concrete, well-understood theoretical framework, offering a serene and clear illustration of these fascinating gravitational phenomena. It guides our understanding of why initial wormhole models remained purely theoretical curiosities. The fundamental reason for its non-traversable nature is that its delicate throat would inevitably pinch off before anything, even a photon of light, could possibly pass through it. This rapid constriction of the wormhole's opening is a direct consequence of the immense gravitational forces at play, which cause the fabric of spacetime itself to collapse in on the pathway with an incredible, almost instantaneous swiftness. Any object attempting to enter this fleeting conduit would find the passage sealed before its journey could even truly begin, trapped by the relentless dynamics of extreme gravity. This inherent instability means that the Schwarzschild wormhole, while a mathematically profound solution, offers no practical means for cosmic travel. It remains a serene yet firm reminder of the universe's architectural limitations, demonstrating that while spacetime can be bent and folded in theory, the conditions for a stable, traversable tunnel are exceptionally stringent. The swift and gentle closure of this cosmic passage underscores the quiet power of gravity. The swift and gentle. This inherent ephemeral nature of the initial Einstein-Rosen bridges spurred further theoretical exploration, leading to a more ambitious and captivating concept, the traversable wormhole. The idea of such a pathway was significantly popularized by the distinguished theoretical physicist Kip Thorne during the 1980s. Thorne's involvement arose from a request by the renowned astronomer Carl Sagan, who was seeking scientifically plausible methods for interstellar travel for his novel, Contact. This collaboration brought the once abstract mathematical curiosity into a more tangible, albeit still theoretical realm, sparking widespread imagination and rigorous scientific inquiry. Thorne's research illuminated the profound distinction between a fleeting gravitational anomaly and a potentially navigable cosmic thoroughfare, transforming the discussion from pure mathematical curiosity into a contemplation of a true cosmic pathway. This marked a serene, yet significant shift in how scientists approach the enigmatic concept, inviting a deeper dive into the universe's potential for shortcuts. The gentle push of scientific curiosity, even when inspired by fiction, can lead to profound theoretical advancements, patiently unfolding new possibilities within the cosmic tapestry. This intellectual journey, initiated by the desire to bridge cosmic distances, allowed for the calm contemplation of spacetime's deepest secrets, revealing how the very fabric of our reality might be subtly manipulated. The exploration of these theoretical pathways continues to unfold, much like a placid cosmic river, revealing new dimensions of thought with each bend, gently expanding the horizons of our cosmic understanding. These highly sought-after traversable wormholes would, by their very definition, possess the extraordinary capacity to allow matter, and perhaps even living beings, such as people, to pass safely and serenely from one end to the other. Unlike their non-traversable predecessors, which would vanish in an instant, these theoretical conduits would maintain a stable opening, providing a clear and enduring path. Imagine a tranquil, unhurried journey through a cosmic tunnel, where the immense distances between stars and galaxies are compressed into a manageable passage. This vision offers a calm alternative to the arduous, multi-generational voyages that conventional space travel would entail for interstellar distances. The very essence of a traversable wormhole is its ability to preserve the integrity of any object or individual passing through it, protecting them from the extreme gravitational stresses and instantaneous closure that plague simpler models. This promise of safe transit is what fuels much of the scientific and popular fascination, envisioning a future where the cosmos is no longer an insurmountable barrier, but a connected network of accessible destinations, traversable with a quiet grace. The concept allows for a serene dream of reaching distant star systems, carried by the subtle curves of space-time itself, gently guiding us to new horizons. This capacity for safe passage represents a profound leap in theoretical cosmic navigation, offering a serene solution to the otherwise daunting challenge of traversing the universe's vastness. The elegance of such a pathway lies in its potential to transform our understanding of cosmic travel from a distant dream into a deeply considered theoretical possibility, inviting us to ponder journeys that are both swift and profoundly peaceful, a tranquil ballet of physics and imagination. For such a miraculous journey to be feasible, a traversable wormhole would critically require a stable throat, a persistent opening that does not collapse instantly under its own gravitational forces. This stable configuration is the cornerstone of its utility, transforming a fleeting theoretical flicker into a sustained cosmic pathway. Without this stability, the wormhole would revert to the non-traversable type, pinching shut with the speed of light, rendering any passage impossible. Maintaining this open throat demands a delicate balance of gravitational influences, essentially holding open a tear in space-time. It is a profound engineering challenge, even in theoretical terms, requiring a mechanism that actively resists the natural tendency of such extreme curvatures to collapse. This stability would create an enduring passage, a placid corridor through the universe, allowing for a leisurely drift from one cosmic point to another. The very thought of such a sustained opening invites us to ponder the immense forces and subtle energies that would be needed to sculpt space-time into such a welcoming form, a testament to the universe's potential for intricate yet serene structures. The sustained presence of this theoretical throat is what elevates the concept from a mere mathematical curiosity to a potential avenue for cosmic exploration, allowing for a tranquil and unhurried passage through the depths of space. This quiet steadfastness is essential, ensuring that any journey would be one of smooth continuity rather than abrupt cessation, a testament to the patient unfolding of cosmic possibilities. Furthermore, such a traversable wormhole could theoretically connect two distinctly different points within our expansive universe. Picture two galaxies, separated by millions of light years, suddenly brought into intimate proximity through a single stable wormhole. This would mean that a journey that would otherwise consume countless millennia, even at the speed of light, could potentially be completed in a matter of hours, or perhaps days, depending on the wormhole's configuration. It transforms the universe from an overwhelmingly vast and fragmented collection of distant realms into a more interconnected, manageable space. This ability to bridge immense cosmic gulfs with such elegance is what makes wormholes so captivating to scientists and dreamers alike. It offers a serene vision of interstellar communion, where the quiet solitude of deep space is gently overcome by the presence of a direct, navigable pathway. The subtle weaving of space-time would allow for a tranquil, abbreviated journey across the cosmic tapestry, connecting stellar systems that are otherwise separated by an almost unimaginable expanse. This theoretical link promises a future where the universe feels less isolated, more like a grand, interconnected garden, where every distant star system is but a short, peaceful journey away. The implications for exploration and communication across the cosmos are as vast as the distances they aim to conquer, offering a placid vision of a truly unified cosmic neighborhood, an elegant testament to the creative power of cosmic geometry. Even more profoundly, these theoretical conduits could, in certain configurations, connect two distinctly different points in time. This extraordinary possibility emerges from the intricate interplay between gravity and the four-dimensional nature of space-time. If one mouth of a traversable wormhole were to be moved at near the speed of light and then returned, the effects of time dilation, as predicted by special relativity, could cause a temporal disparity between its two ends. This means that a traveler entering one mouth could potentially emerge at an earlier or later point in time relative to the other mouth, This aspect introduces the mind-bending concept of time travel, opening up a serene yet complex realm of theoretical possibilities and paradoxes. It challenges our linear perception of time, suggesting that the universe's fabric might permit journeys not just across space, but through the very moments of its history. This elegant, albeit speculative, capability adds another layer of profound wonder to the wormhole concept, inviting us to contemplate the universe's unhurried flow and its potential for unexpected temporal pathways, a quiet dance through cosmic epochs. The idea of revisiting the universe's past or glimpsing its future through such a gentle cosmic tunnel stirs a deep sense of tranquil awe, expanding our understanding of reality's pliable nature. It is a concept that, while challenging, remains a placid area of deep theoretical inquiry, patiently explored by those who seek to understand the universe's most intricate secrets, revealing the subtle elasticity of time itself. To clearly differentiate these stable, potentially navigable pathways from their fleeting predecessors, they are sometimes referred to as Lorentzian wormholes, a term that gently distinguishes them from the original, non-traversable type. These Lorentzian pathways represent a more refined and enduring vision of cosmic connection, offering a sustained and serene passage through the intricate tapestry of space-time, unlike the ephemeral Einstein-Rosen bridges that snap shut instantly. The very name evokes a sense of enduring structure, a cosmic thoroughfare thoughtfully designed to remain open for the duration of a journey, allowing for a tranquil and unhurried transit. This distinction is crucial for understanding the profound difference between a mere mathematical curiosity and a theoretical device that could genuinely facilitate interstellar or even intertemporal travel, allowing for a calm, purposeful movement across the universe's grand design. The shift in nomenclature reflects a deeper theoretical understanding, moving from fleeting possibility to a more robust, albeit still speculative, concept of a cosmic gateway. Now, to maintain such an extraordinary opening, to keep a wormhole open and truly traversable, a very special and profoundly unusual type of substance is required. One that physicists have termed exotic matter. This isn't the ordinary matter that makes up stars, planets, or even ourselves. It's a theoretical construct with properties that challenge our everyday understanding of the universe. Without the continuous presence of this enigmatic material, the immense gravitational forces inherent in such a curved region of space-time would cause the wormhole's delicate throat to instantly collapse, much like the non-traversable models we previously discussed. The exotic matter acts as a cosmic scaffolding, holding open the passage against its natural tendency to pinch shut, ensuring a stable and enduring pathway for any potential cosmic voyager. It's a serene act of subtle cosmic engineering, a theoretical requirement that underscores the extraordinary nature of these proposed shortcuts. The existence of such a stable conduit would transform our perception of cosmic distances, allowing for a tranquil bridging of vast interstellar gulfs, turning what seems impossibly far into a journey of serene, unhurried transit. This persistent stability is the quiet key to unlocking the wormhole's profound potential, enabling a gentle, continuous flow of passage through the universe's intricate architecture. What makes this exotic matter so profoundly distinct is its possession of negative energy density, a property utterly unlike any known ordinary matter we encounter in the universe. In our familiar world, all matter and energy, from the smallest atom to the grandest galaxy, possess a positive energy density, meaning they contribute to gravitational attraction. This positive energy is what causes objects to draw together, creating the gentle pull we experience as gravity. However, exotic matter would exhibit the opposite effect. Imagine a substance that, instead of adding to the gravitational pull, somehow subtracts from it, creating a localized region where the energy density falls below zero. This concept is deeply counterintuitive, yet it is precisely this unique characteristic that makes exotic matter indispensable for the stability of a traversable wormhole. It's a quiet challenge to our fundamental assumptions about the nature of reality, inviting us to consider forms of energy that lie beyond our everyday experience, yet which could profoundly reshape the cosmos. The very notion of negative energy density whispers of a universe far more subtle and complex than we might initially perceive, with hidden potential to manipulate space-time in astonishing ways. This subtle, almost imperceptible quality is the theoretical anchor for a wormhole's lasting presence, allowing it to defy the universe's natural tendency to smooth out such profound curvatures. This extraordinary negative energy, inherent in exotic matter, would exert a unique and profound repulsive gravitational force. Instead of drawing things inward, as ordinary gravity does, this force would gently push outward, actively preventing the wormhole's delicate throat from collapsing under its own immense gravitational pull. Think of it as an anti-gravitational pressure, a subtle but persistent push that counteracts the universe's natural tendency for highly curved space-time to pinch itself off. This repulsive effect is precisely what is needed to maintain the stable, open structure of a traversable wormhole, creating a sustained corridor through the cosmos. It would act like an invisible, ethereal spring, holding the cosmic passage wide enough for matter and light to pass through unhindered. This concept elegantly solves the problem of instantaneous collapse, allowing for the theoretical possibility of a stable, navigable shortcut across the universe. The serene balance between the attractive force of ordinary gravity and the repulsive force of this exotic matter would create a placid, enduring tunnel, a testament to the intricate interplay of cosmic forces. This gentle repulsion is the key to unlocking the wormhole's potential, transforming it from a fleeting mathematical curiosity into a sustained theoretical pathway, allowing for a serene and graceful passage across the cosmic expanse. While truly exotic matter remains largely theoretical, scientists have, with quiet precision, observed a real-world quantum phenomenon that produces a tiny, almost imperceptible amount of negative energy density in a controlled laboratory setting. This intriguing effect is known as the Casimir effect. It occurs when two uncharged parallel metallic plates are placed extremely close to each other in a vacuum. Quantum theory suggests that even empty space is filled with fleeting virtual particles that constantly pop into and out of existence. Between the plates, only virtual particles with wavelengths small enough to fit can exist, while outside, virtual particles of all wavelengths are present. This subtle difference in quantum fluctuations creates a slightly lower energy density between the plates compared to the outside, resulting in a minuscule net attractive force between the plates. Crucially, the region between the plates can be described as having a tiny amount of negative energy density. This delicate effect, while incredibly small and observed only under highly specific conditions, offers a placid glimpse into the possibility of negative energy within the universe, suggesting it is not entirely forbidden by the laws of physics. It is a quiet confirmation that the concept, though challenging, has a subtle footing in observable reality, even if on an imperceptibly minute scale. This gentle, almost imperceptible phenomenon provides a theoretical whisper of the universe's potential for such unusual energies. However, despite the tantalizing existence of the Casimir effect, the amount of exotic matter needed to stabilize a macroscopic wormhole, one large enough for a spacecraft or even a human being to safely traverse, would be truly immense. The tiny, almost immeasurable quantities of negative energy generated in a laboratory setting are orders of magnitude too small to counteract the colossal gravitational forces that would be at play within a cosmic-scale wormhole. To hold open a stable passage spanning light years, or even just kilometers, would require a vast sea of this enigmatic substance, far exceeding anything we currently understand or believe to be naturally occurring. Imagine trying to hold open a gigantic cosmic doorway with a whisper of a breeze. The scale of the challenge becomes clear. This immense requirement presents a profound hurdle to the practical realization of wormholes, moving them firmly from the realm of the theoretically possible into the domain of the currently unfeasible. It's a serene reminder of the universe's grand scale and the colossal energies required to manipulate its fundamental structure. A quiet testament to the enduring power of gravity. The sheer volume of exotic matter needed underscores the extraordinary nature of such a cosmic engineering feat, patiently revealing the vast chasm between theoretical possibility and practical cosmic reality. This quiet, almost insurmountable obstacle guides our contemplative understanding of the universe's profound limits. Consequently, many scientists quietly believe that truly exotic matter, possessing negative energy density in sufficient quantities to stabilize a macroscopic wormhole, may simply not exist in abundance in nature. While the Casimir effect provides a glimmer of hope that negative energy is not entirely forbidden, the universe, as we observe it, appears to be overwhelmingly dominated by matter and energy with positive density. There is no known natural process that would generate or sustain the vast amounts of exotic matter required to keep a cosmic-sized wormhole open. This scientific consensus, while not an absolute prohibition, suggests that wormholes, if they exist at all, are likely to be fleeting, microscopic, or require conditions far beyond our current understanding. It's a serene acceptance of the universe's current design, acknowledging that some theoretical possibilities, though elegant, may not align with observable reality. This quiet belief in the scarcity of exotic matter humbly guides our expectations, framing wormholes as profound theoretical curiosities rather than readily available cosmic thoroughfares. The gentle unfolding of cosmic laws seems to favor a universe without such readily accessible shortcuts, preserving the immense distances as a testament to its grandeur. This patient understanding allows us to appreciate the universe in its current, magnificent form. Ultimately, the very concept of exotic matter and its profound role in stabilizing wormholes profoundly challenges our understanding of conventional physics and the fundamental energy conditions that underpin our current cosmological models. Energy conditions are a set of assumptions in general relativity that describe the reasonable physical properties of matter and energy, usually stating that energy density and often pressure must be positive. These conditions are deeply ingrained in our understanding of how gravity behaves and how space-time evolves. Exotic matter, by definition, violates these conditions, pushing the boundaries of what is considered physically plausible. This theoretical necessity forces physicists to calmly reevaluate the foundational principles of the universe, questioning whether these energy conditions are universally applicable, or if there are subtle ways they might be circumvented under extreme, as yet undiscovered circumstances. It is a serene intellectual frontier, where the pursuit of wormholes leads to a deeper, more nuanced understanding of the universe's most fundamental laws. This quiet defiance of conventional physics invites us to explore new theoretical landscapes, patiently expanding the delicate boundaries of cosmic comprehension. The challenge it poses is not one of conflict, but of serene intellectual growth, guiding us toward a more complete and subtle understanding of the universe's intricate design. This profound contemplation helps us to gently redefine the limits of what is possible within the vast cosmic tapestry. Even with the theoretical availability of this remarkable exotic matter, the challenge of maintaining a stable wormhole would still represent an engineering marvel of almost unimaginable scale. It is not merely enough to possess the substance with negative energy density. One must precisely place it, meticulously control its distribution, and ensure its long-term stability against the inherent cosmic forces. The universe, in its majestic indifference, constantly seeks equilibrium, and holding open such an extreme distortion of space-time would require a continuous, delicate balancing act. This would demand a level of technological sophistication far beyond anything humanity currently conceives, a triumph of theoretical physics translated into a serene, yet robust, cosmic structure. Imagine shaping the very fabric of reality to create a lasting pathway. Such a feat would stand as a quiet testament to the ultimate mastery of cosmic mechanics, a truly placid demonstration of advanced civilization. The calm precision needed for such an endeavor speaks to the subtle complexities inherent in manipulating the universe's fundamental laws, patiently guiding us toward an understanding of its deepest secrets. This intricate dance between theoretical possibility and practical realization highlights the profound elegance of cosmic engineering, even in its hypothetical form. Without the precise influence of exotic matter, the wormhole's delicate throat would, as we have explored, instantly collapse with the unyielding swiftness of the speed of light. This immediate and inevitable closure underscores the critical role that exotic matter plays in the very concept of a traversable wormhole. The natural gravitational pull of the wormhole's own structure, left unchecked, would cause the space-time fabric to pinch off, sealing the pathway before any particle, let alone a spacecraft, could even begin its journey. This rapid and irreversible sealing would render the wormhole utterly non-functional as a shortcut, reducing it once more to a mere mathematical curiosity. The inherent fragility of space-time under such extreme curvatures necessitates an active, repulsive force to maintain an open passage. It is a silent cosmic law that demands extraordinary conditions for extraordinary phenomena. The absence of this stabilizing influence would result in a swift, almost imperceptible disappearance of the cosmic conduit, a gentle yet firm declaration by the universe that some shortcuts require very specific and perhaps unattainable conditions. This swift closure, occurring at the universe's ultimate speed limit, patiently reminds us of the delicate balance required for any enduring cosmic structure, guiding our understanding of spacetime's profound dynamics. Despite the profound implications of wormholes as cosmic shortcuts, the journey through a wormhole would not be instantaneous, a common misconception often portrayed in popular imagination. While a wormhole dramatically reduces the effective distance between 2 points, the act of traversing the wormhole itself would still take a measurable amount of time. It is not a magical teleportation device, but rather a compressed pathway. However, this journey could indeed be much faster than conventional space travel, which would require traversing the vast, intervening light years of normal space. For instance, a trip that might take thousands or millions of years using traditional propulsion, even at speeds approaching days or weeks through a stable wormhole. This profound reduction in travel time is what makes the concept so appealing for interstellar exploration, transforming daunting cosmic voyages into journeys of manageable duration. It offers a serene vision of accelerated cosmic travel, allowing for a tranquil and efficient passage across the immense gulfs separating star systems. The unhurried progression through the wormhole itself, while not instantaneous, still represents an extraordinary leap in cosmic navigation, gently bridging the vast distances of the universe with a newfound elegance. This quiet acceleration of travel profoundly redefines the scale of cosmic accessibility. The precise duration of travel through a wormhole would elegantly depend on several key factors, primarily the wormhole's internal length and its specific configuration. Unlike a simple point-to-point jump, a wormhole might possess a measurable tunnel or throat that extends through a region of highly curved spacetime. A shorter, more direct internal pathway would naturally allow for a quicker transit, while a longer, more winding configuration would extend the journey. Additionally, the way spacetime is curved within the wormhole, influenced by the distribution of the exotic matter, would also play a subtle role in determining the travel time. Scientists believe that the internal geometry of a wormhole could be quite complex, much like a cosmic river with varying currents and lengths. This nuanced understanding of travel time ensures that while wormholes offer shortcuts, they still adhere to the fundamental principle that traversing any distance, however compressed, requires a certain passage of moments. The unhurried flow through such a pathway would be governed by these internal characteristics, offering a serene, predictable journey. This quiet dependence on internal geometry reminds us that even theoretical cosmic shortcuts possess their own intricate design, patiently revealing the subtle complexities of spacetime's architecture. However, a significant and potentially perilous challenge for any voyager would be the presence of extreme tidal forces near the wormhole's mouth, forces capable of stretching an object or even a person to an agonizing degree. Tidal forces arise from differences in gravitational pull across an object's length. Near an intensely curved region of spacetime, such as the entrance to a wormhole, the gravitational pull on one part of a body could be vastly stronger than on another. This differential force would cause the object to be elongated, stretched thin like spaghetti, a process sometimes vividly, though calmly, referred to as spaghettification. This phenomenon, also associated with the extreme gravity of black holes, poses a severe threat to any form of safe passage. For a human or a spacecraft to survive such a journey, these stretching forces would need to be mitigated to an almost imperceptible level. It's a serene reminder that while wormholes offer incredible possibilities, they also present profound dangers, demanding careful consideration of gravitational effects. The delicate balance between cosmic wonder and inherent peril highlights the universe's subtle, yet powerful, gravitational dynamics, patiently revealing the challenges of traversing extreme space-time curvatures. The quiet threat of these forces underscores the need for meticulous theoretical design for any safe passage. Therefore, for any hope of safe passage through such a cosmic conduit, the wormhole's throat, its entrance and internal pathway, would need to be very wide. A narrow throat would mean that the gravitational gradients, the changes in gravitational pull over short distances, would be extremely steep. These steep gradients are precisely what generate the dangerous tidal forces that could tear an object apart. By contrast, a significantly wider throat would allow for a much gentler curve in spacetime, distributing the gravitational forces more evenly across a traversing object. This increased width would provide a more placid and uniform gravitational environment, reducing the stretching effects to a tolerable level for a human or a delicate spacecraft. It's a serene design principle. The larger the opening, the smoother and safer the transition. This requirement for immense size further emphasizes the colossal scale of exotic matter that would be necessary to hold such a vast passage open. The quiet grandeur of a wide wormhole throat speaks to the theoretical ambition of such cosmic engineering, patiently revealing the profound connections between safety and scale in the universe's most extreme structures. Indeed, a wider throat would directly serve to reduce the dangerous tidal forces to a tolerable level, making a journey through the wormhole not only possible, but also serene and comfortable. When the space-time curvature is spread out over a larger expanse, the differential gravitational pull across a traveler's body becomes less pronounced. This means that instead of being violently stretched, an object would experience only a gentle, uniform squeeze or pull, well within the limits of biological or structural integrity. Imagine drifting through a vast, ethereal tunnel where the gravitational embrace is soft and even, rather than sharp and distorting. This condition is paramount for any form of life to survive the passage, transforming the theoretical journey from a perilous ordeal into a tranquil cosmic voyage. The elegant design of a wide-mouthed wormhole, stabilized by sufficient exotic matter, promises a peaceful transit where the immense distances of the universe are overcome with a quiet grace. This careful mitigation of tidal forces is a crucial step in envisioning truly navigable wormholes, allowing for a serene and unhurried passage through the profound depths of space-time, patiently unveiling the universe's potential for gentle yet powerful shortcuts. The serene promise of a safe journey through a wide wormhole speaks to the careful balance of forces required for cosmic voyaging. Thus, the theoretical journey through a wormhole, while not a momentary event, holds the promise of dramatically accelerated travel across the cosmos. This intricate balance of stability, exotic matter, and careful architectural design for the wormhole's throat paints a captivating picture of what might one day be possible. It is a quiet testament to humanity's enduring curiosity, pushing the boundaries of what we understand about the universe's fundamental laws. The concept of a wormhole, therefore, continues to inspire, offering a serene glimpse into a future where the vastness of space becomes a little less daunting, and the stars a little closer within reach, all through the elegant manipulation of space-time itself. The unhurried pace of scientific discovery continues to explore these profound possibilities, leading us to one of the most intriguing and mind-bending aspects of traversable wormholes: their potential connection to time travel. Imagine the tranquil flow of time, usually an unyielding progression forward, becoming something pliable, something that could be gently navigated. This fascinating prospect emerges accelerated to near light speed and then gently returned to its original position. The core principle behind this phenomenon lies in Einstein's theory of special relativity, which beautifully describes how time itself can dilate or slow down for objects moving at extreme velocities relative to an observer. If one end of a wormhole were to undertake such a swift cosmic journey, experiencing significant time dilation, it would effectively age less than its stationary counterpart. When the moving mouth returned, a temporal disparity would exist between the two ends. A traveler entering the mouth that had remained stationary would emerge from the mouth that had journeyed, but at a point in time before they entered, thus creating a pathway into the past. This serene yet complex manipulation of space-time's temporal dimension opens up a quiet realm of theoretical possibilities that profoundly challenge our linear understanding of time. It suggests a universe where time is not merely a relentless river flowing in one direction, but a vast, calm ocean with hidden currents, some of which might lead to earlier shores. The elegant interplay of speed and time, as described by relativity, offers a placid and thought-provoking vision of temporal navigation, a testament to the subtle flexibility of the cosmic clock. This theoretical mechanism, while requiring immense energy and advanced technology, invites us to calmly consider the universe's most profound secrets, revealing how the very fabric of reality might hold keys to unlocking temporal journeys. This extraordinary configuration, involving the acceleration and return of one wormhole mouth, could theoretically allow for travel into the past. Picture a scenario where a spacecraft enters the stationary mouth of a wormhole, travels through its stable throat, and emerges from the mouth that has experienced time dilation due to its high-speed journey. Because the moving mouth aged less, the moment of emergence would correspond to an earlier point in time, relative to the moment the traveler entered the stationary mouth. This creates a closed loop in space-time, a pathway where one could, in principle, revisit moments that have already transpired. The implications of such a capability are as vast as they are unsettling, gently cause and effect. It is a serene, yet profound, theoretical opening into the annals of cosmic history, offering a quiet glimpse into epochs long past. The very idea of stepping back into time, observing or even interacting with prior events, presents a captivating challenge to our conventional understanding of reality's progression. This theoretical journey into the past, while seemingly miraculous, arises directly from the elegant equations of general relativity, showcasing the profound and sometimes counterintuitive consequences of manipulating space-time. It invites a calm contemplation of the universe's temporal structure, revealing its potential for intricate, non-linear pathways, a testament to the subtle elasticity of time's flow. The tranquil possibility of such backward movement inspires both wonder and careful consideration. However, such theoretical time travel, particularly into the past, immediately brings forth a host of profound and unsettling questions, often leading to conceptual dilemmas known as paradoxes. The most famous of these is the grandfather paradox. This thought experiment calmly asks, what if a traveler journeyed into the past through a wormhole and, by some action, prevented their own grandfather from meeting their grandmother? If this were to happen, then the traveler's parent would never have been born, and consequently, the traveler themselves would never have existed. If the traveler never existed, then they could not have journeyed into the past to prevent their grandfather from meeting their grandmother in the first place. This creates an impossible logical contradiction, a serene loop of non-existence that defies causality. Such paradoxes highlight the deep tension between the theoretical possibilities of time travel and our intuitive understanding of how events unfold in a consistent and logical sequence. They invite a quiet contemplation of the universe's fundamental rules, suggesting that there might be inherent mechanisms that safeguard the integrity of the timeline. The very existence of these paradoxes gently pushes physicists to seek deeper explanations or subtle restrictions within the laws of physics that might prevent such causal violations. This serene exploration of logical inconsistencies underscores the profound challenges in reconciling time travel with a coherent and stable reality, patiently revealing the intricate web of cause and effect in the cosmic tapestry. In response to these profound paradoxes, and with a deep sense of the universe's inherent order, the renowned theoretical physicist Stephen Hawking proposed a fascinating concept known as the chronology protection conjecture. This conjecture quietly suggests that the laws of physics might inherently conspire to prevent time travel on macroscopic scales, thereby safeguarding the universe from the logical inconsistencies that paradoxes would entail. It's not a formal proof, but rather a profound intuition, an elegant suggestion that nature itself might possess a subtle, self-correcting mechanism. Hawking believed that any attempt to create a time machine, such as a traversable wormhole configured for backward time travel, would be met with an insurmountable physical barrier. This barrier might manifest as an uncontrolled surge of radiation, an exponential growth of quantum fluctuations, or some other unforeseen physical phenomenon that would destroy the time machine before it could ever become functional. This conjecture offers a serene resolution to the paradox problem, implying that the universe is fundamentally stable and self-consistent, gently preventing any actions that could unravel its causal fabric. It is a quiet testament to the universe's profound elegance, ensuring its smooth and logical progression through time. This patient conjecture guides our understanding toward an inherent cosmic wisdom that maintains order and prevents chaos. This profound chronology protection conjecture, therefore, implies that nature might, in its serene wisdom, find an elegant way to make time travel into the past impossible. It's a subtle but powerful assertion that the universe has an intrinsic resistance to causal violations. Rather than explicitly forbidding time travel through a specific law, the conjecture suggests a more nuanced, dynamic process. Imagine the universe as a vast, self-regulating system that subtly adjusts its parameters to ensure a consistent timeline. Any attempt to create a closed time-like curve, the theoretical pathway for time travel, would be met with an overwhelming counterforce generated by the very fabric of spacetime and quantum fields. This might involve a surge of virtual particles or an instability in the exotic matter required to keep the wormhole open, effectively sabotaging the time machine before it can fulfill its purpose. This gentle, yet firm, cosmic defense mechanism would preserve the integrity of causality, ensuring that the past remains inviolable. It offers a placid resolution to the dizzying array of paradoxes, allowing us to calmly contemplate the universe's unwavering commitment to its own logical consistency. This quiet implication underscores the profound elegance of cosmic self-preservation, patiently revealing the universe's intrinsic order and its subtle ways of maintaining temporal harmony. At the very heart of the theoretical possibility of time travel through wormholes lies the concept of closed, time-like curves. These are not merely abstract ideas, but precise mathematical constructs within general relativity, representing paths in spacetime that loop back to an earlier point in time. Imagine a journey through spacetime that, instead of always moving forward, eventually brings you back to your starting point in the past. Such a curve would allow an object or a person to return to a previous moment, effectively traversing their own history. Wormholes, when configured in specific ways, particularly by the differential aging of their mouths, are one of the leading theoretical candidates for creating these closed time-like curves. They offer a serene, elegant mechanism for bending space-time in such a way that time itself forms a closed loop. This concept is the theoretical foundation upon which all wormhole-based time travel rests, providing the rigorous mathematical framework for exploring these mind-bending possibilities. It is a quiet testament to the profound flexibility of space-time, patiently revealing how its intricate geometry could, in theory, allow for existence, challenging our linear perceptions of reality. Indeed, such closed time-like curves are the profound theoretical foundation for time travel within the framework of general relativity. The mathematical equations of Einstein's theory do not explicitly forbid these loops in spacetime, which is why the concept of time travel, however paradoxical, remains a persistent area of scientific inquiry. These curves represent a direct pathway to the past, a trajectory through the universe that allows for a return to an earlier moment. While general relativity allows for the existence of such curves under extreme conditions, it does not necessarily guarantee their formation or stability in a physically plausible manner. This distinction is crucial, as the existence of a mathematical solution does not always equate to a naturally occurring or easily engineered phenomenon. The careful study of closed time-like curves pushes the boundaries of our understanding of spacetime, inviting us to calmly explore the universe's most intricate and challenging theoretical possibilities. It is a serene intellectual journey into the heart of cosmic causality, patiently seeking to understand the deep connections between space, time, and the fundamental laws that govern their interplay. The theoretical elegance of these curves provides a placid canvas for exploring the universe's most profound temporal secrets, guiding us toward a more complete understanding of its subtle and often counterintuitive nature. Beyond the grand theoretical visions of traversable wormholes, some intriguing theories suggest that microscopic wormholes might constantly form and vanish at the quantum level, a phenomenon often referred to as space-time foam. Imagine the universe's fabric not as an entirely smooth and unchanging canvas, but as a turbulent, bubbling sea at the tiniest, most fundamental scales. At these infinitesimal dimensions, far smaller than an atom, quantum mechanics dictates that energy and matter fluctuate wildly, giving rise to fleeting, ephemeral distortions in spacetime. These distortions could, in theory, manifest as minuscule wormholes, briefly connecting different points in this subatomic realm before dissolving back into the quantum froth. It's a serene vision of the universe at its most fundamental, a quiet dance of creation and annihilation happening on scales utterly imperceptible to our senses, yet potentially shaping the very essence of reality. This conceptual foam suggests that the universe is far more dynamic and intricately woven than its calm, macroscopic appearance might suggest, offering a placid glimpse into its deepest quantum mysteries. The constant, unhurried formation and dissolution of these tiny structures paint a picture of ceaseless, subtle activity at the very foundations of existence, a gentle, vibrant hum beneath the cosmic silence. However, it is crucial to understand that even if these quantum wormholes do indeed exist, they would be far too small and incredibly unstable for any practical use whatsoever. These fleeting connections would exist for durations so infinitesimally brief that they would vanish almost instantly, far before any information or particle could traverse them. Their size, measured in what physicists call the Planck length, an unimaginably small scale roughly 1/1,000,000th of a billionth meter, makes them utterly inaccessible to any form of macroscopic interaction. They are the cosmic equivalent of bubbles that pop into existence and disappear in the blink of an eye, offering no stable pathway for anything larger than the most fundamental particles, and even then, only for the briefest of moments. Therefore, while their theoretical existence is fascinating for understanding quantum gravity, these quantum wormholes hold no promise for interstellar travel or time manipulation. They serve as a serene reminder of the universe's scale, where even the most exotic phenomena at one extreme are profoundly irrelevant at another, maintaining a quiet, elegant separation between the quantum and the cosmic. This inherent instability and minuscule scale gently guide our expectations, revealing the limits of even the most profound theoretical possibilities. Shifting our gaze from the quantum realm to the grand sweep of cosmic history, another intriguing possibility is that primordial wormholes might have formed in the extreme, tumultuous conditions of the very early universe. In the moments immediately following the Big Bang, the cosmos was a place of unimaginable density and energy, a state far removed from the placid, expansive universe we observe today. During these initial epochs, space-time itself was undergoing rapid and profound transformations. Scientists ponder whether these intense, fleeting conditions could have naturally given rise to tiny, stable wormholes, perhaps even without the need for exotic matter as we understand it for macroscopic tunnels. If such wormholes did indeed form, they would be relics, ancient gravitational fossils from the universe's infancy, scattered across the cosmos like precious silent whispers of its fiery birth. These primordial pathways, if they exist, would offer a unique window into the fundamental physics that governed the universe when it was just a fraction of a second old, providing invaluable clues about its origins and early evolution. The serene contemplation of such ancient cosmic structures invites us to ponder the universe's initial state, revealing how its earliest moments might have sculpted lasting, though hidden, features within its grand design. This quiet hypothesis connects the deepest past to the present, offering a placid potential for discovery. Despite the captivating theoretical allure of wormholes, both quantum and primordial, it remains a steadfast scientific truth that no direct observational evidence for any type of wormhole has ever been found in the vast and silent cosmos. Astronomers, with their ever-improving telescopes and sophisticated instruments, diligently scan the heavens, searching for anomalies or subtle space-time tunnels. Yet, thus far, the universe has maintained its enigmatic silence on the matter. There have been no confirmed sightings, no peculiar patterns of light, and no direct gravitational signals that unequivocally point to a wormhole's solutions within the equations of general relativity, and as captivating subjects of theoretical inquiry, rather than observed features of the cosmic landscape. This absence of direct evidence serves as a serene reminder of the immense challenges in probing the universe's most extreme and subtle phenomena, patiently highlighting the gap between theoretical possibility and empirical confirmation. The quiet expanse of space continues to guard its, maintaining a placid balance between scientific imagination and observable reality. While direct observation remains elusive, scientists calmly consider how indirect detection might be achieved, primarily by observing peculiar gravitational lensing effects. Gravitational lensing is a phenomenon where the immense gravity of massive objects, such as galaxies or galaxy clusters, bends and distorts the light from more distant objects, much like a cosmic magnifying glass. A wormhole, with its extreme curvature of space-time, would also bend light, but in a unique and potentially discernible way, different from the lensing patterns produced by ordinary black holes or massive galaxies. Imagine light from a distant star or galaxy traveling towards us, only to pass near the mouth of a hidden wormhole. The wormhole's distinct gravitational field would subtly warp the light's path, creating a characteristic distortion that astronomers might be able to detect. This method offers a serene and patient approach, relying on the universe's own light to reveal its hidden structures. The careful analysis of these subtle distortions could provide the first indirect whispers of a wormhole's presence, a placid clue woven into the grand tapestry of cosmic light. This quiet search for gravitational anomalies continues to refine our observational techniques. Elaborating on this fascinating possibility, a wormhole's mouth might appear to us as a profoundly distorted view of another entirely different region of space. Instead of seeing the familiar stars and galaxies that lie directly behind the wormhole in our line of sight, we might observe images of celestial objects from a completely separate, distant part of the universe, or even from another point in time. Imagine gazing through a cosmic window only to see a scene from a faraway galaxy, seemingly floating in an impossible position, or perhaps even a younger version of a galaxy we know. This visual anomaly would be akin to looking through a bizarre, ethereal lens that refracts light in an utterly unconventional manner, creating a surreal and captivating cosmic mirage. The light from these distant regions would have traveled through the wormhole's throat, emerging from its mouth to greet our telescopes. Such a peculiar optical signature would be a strong, albeit indirect, indicator of a wormhole's presence, offering a serene and beautiful confirmation of its space-time bending properties. This placid visual distortion would provide a unique fingerprint, guiding astronomers toward the location of these elusive cosmic shortcuts, unveiling the universe's hidden connections with a quiet elegance. Beyond light distortions, another potential avenue for detection lies in the gravitational wave signatures that could potentially be emitted by unstable or forming wormholes. Gravitational waves are ripples in the very fabric of space-time, generated by the acceleration of massive objects, such as merging black holes or neutron stars. These waves travel across the cosmos, carrying information about the most energetic events in the universe. If a wormhole were to form, perhaps in the extreme conditions of the early universe or near a collapsing star, the intense dynamics involved could generate a burst of distinctive gravitational waves. Similarly, an unstable wormhole undergoing a rapid collapse, or even objects interacting in a peculiar way within its vicinity, might emit unique patterns of these space-time ripples. Scientists are developing sophisticated gravitational wave observatories, like LIGO and Virgo, which are designed to detect these subtle cosmic vibrations. The challenge lies in distinguishing the unique signature of a wormhole from the more familiar signals of black hole mergers or other astrophysical phenomena. However, if detected, these gravitational wave whispers would provide profound insights into the formation and behavior of wormholes, offering a serene and powerful testament to their existence. This quiet symphony of space-time, if it contains wormhole melodies, would be a momentous discovery, patiently revealing the universe's most intricate and energetic secrets. The search for these subtle tremors continues, offering a placid promise of future revelations. Thus, while wormholes remain firmly in the realm of theory and speculation, the scientific community continues its calm and diligent search for any subtle hints of their existence. From the minuscule quantum foam to the grandest cosmic events, the universe might hold these hidden pathways. The pursuit of these elusive structures, whether through the delicate analysis of light distortions or the patient listening for gravitational whispers, underscores humanity's enduring quest to understand the profound and often counterintuitive nature of space-time itself. This serene journey of discovery, even when faced with the absence of direct evidence, continues to expand our understanding of the cosmos's deepest and most elegant secrets. The quiet persistence of scientific inquiry ensures that these profound possibilities remain a vibrant part of our cosmic contemplation. As we delve deeper into the theoretical landscape of space-time, it becomes essential to gently distinguish between concepts that, while both born from the equations of general relativity, possess fundamentally different natures. While often confused, wormholes are indeed fundamentally different from black holes, a distinction crucial for understanding their unique roles in theoretical physics. Both phenomena involve extreme curvatures of space-time. Both challenge our intuitive understanding of gravity, and both are often depicted as mysterious cosmic entities. However, their internal structures, their interaction with matter, and their potential implications for cosmic travel diverge significantly. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape, an ultimate cosmic trap. A traversable wormhole, by contrast, is envisioned as a pathway, a bridge connecting distant regions, specifically designed to allow passage. This serene contrast between an inescapable cosmic attractor and a potential cosmic conduit highlights the delicate nuances of gravitational theory, inviting a calm and precise exploration of their distinct characteristics. One represents an endpoint, a profound conclusion for anything that enters. The other, a theoretical beginning, a new pathway to elsewhere. This subtle divergence in purpose and function is a core element in unraveling the universe's profound gravitational mysteries, patiently guiding our understanding toward a more nuanced appreciation of cosmic structures. A primary and profoundly defining characteristic of black holes is the presence of a singularity at their very center, a point of infinite density. Imagine all the mass of a colossal star, or even a galaxy, compressed into an infinitesimally small volume, a point where the fabric of spacetime is warped to an extreme, almost incomprehensible degree. At this singularity, the laws of physics, as we currently understand them, gracefully break down, reaching limits that our current theories cannot fully describe. It is a place of ultimate compression, a profound gravitational abyss where matter ceases to exist in any familiar form, vanishing into an eternal point. This central singularity is the inescapable endpoint for anything that falls into a black hole, a silent and serene testament to the immense power of gravity when concentrated to its absolute maximum. The journey towards this point is one of increasing gravitational stress, culminating in an ultimate, singular conclusion. This profound internal structure marks a black hole as a cosmic entity of immense and irreversible gravitational power, distinct from the more benign, albeit theoretical pathways of wormholes. The quiet contemplation of this infinite density gently pushes the boundaries of our cosmic understanding, revealing the universe's most extreme gravitational states. Further defining the nature of a black hole is its event horizon, which acts as a profound one-way boundary. Nothing, not even light, can escape once it has crossed this invisible threshold. Picture a serene cosmic veil, an ethereal surface that marks the point of no return. Beyond this boundary, the gravitational pull is so overwhelmingly strong that the escape velocity, the speed needed to break free from its grasp, exceeds the speed of light itself. Since nothing can travel faster than light, anything that passes the event horizon is irrevocably drawn inwards, destined to descend toward the central singularity. It is a cosmic prison, a region of space-time from which all information, all matter, and all light are forever lost to the outside universe. This makes the event horizon a defining, irreversible feature of a black hole, a placid yet unyielding demarcation line. The quiet certainty of this one-way passage underscores the black hole's role as a cosmic absorber, a profound gravitational sink, fundamentally different from any envisioned traversable pathway. The serene, silent crossing of this threshold marks a point of no return, a gentle yet absolute limit within the cosmic journey, patiently revealing the universe's unyielding gravitational laws. In serene and elegant contrast, a traversable wormhole, by its very definition, would allow passage in both directions. Unlike the unidirectional nature of a black hole's event horizon, a wormhole is envisioned as a symmetrical pathway, a true cosmic bridge that can be traversed from either end. One could, in theory, enter one mouth and emerge from the other, and then, with equal ease, journey back through the wormhole to the original starting point. This bidirectional capability is the fundamental reason why wormholes are considered potential shortcuts for interstellar travel. They are not gravitational cul-de-sacs, but rather open conduits, offering a round-trip ticket across vast cosmic distances. This inherent two-way street transforms the concept from a mere gravitational curiosity into a potential tool for exploration and connection, allowing for a serene and unhurried exchange between distant cosmic locales. The elegant symmetry of passage distinguishes the wormhole as a truly unique theoretical construct, providing a placid vision of cosmic connectivity, a gentle pathway across the universe's immense expanse. This crucial difference highlights the wormhole's potential to facilitate interaction, rather than merely absorb it. Adding another layer of profound theoretical intrigue, the ER-EPR conjecture suggests a deep and unexpected connection between wormholes, specifically the Einstein-Rosen bridges, and a peculiar phenomenon in quantum mechanics known as quantum entanglement, famously described by the Einstein-Podolsky-Rosen paradox. The ER in the conjecture refers to the Einstein-Rosen bridge, the original concept of a wormhole, while EPR refers to the Einstein-Podolsky-Rosen paradox, which highlights the seemingly instantaneous, non-local correlation between entangled particles. Quantum entanglement is a mysterious link where two particles become so deeply connected that they share the same fate, no matter how far apart they are. Measuring a property of one instantly influences the other, as if they are communicating faster than light, although no information is actually transmitted faster than light. The ER-EPR conjecture proposes that this profound quantum connection might be geometrically expressed as a tiny, non-traversable wormhole. It's a serene, elegant attempt to bridge the two great pillars of modern physics: general relativity, describing gravity and spacetime, and quantum mechanics, describing the very small. This subtle interplay hints at a deeper, unified understanding of the universe, where the seemingly disparate realms of gravity and quantum reality are intricately woven together, a quiet dance of cosmic forces. The conjecture offers a placid vision of underlying cosmic unity, patiently revealing the profound relationships between the universe's grandest and smallest scales. More specifically, this groundbreaking idea proposes that entangled particles might be connected by tiny, non-traversable wormholes. These are not the macroscopic, traversable wormholes envisioned for interstellar travel, but rather microscopic, ephemeral connections within the fabric of spacetime. Imagine two entangled particles, separated by light years, yet intimately linked. The ER-EPR conjecture suggests that this instantaneous quantum correlation might be physically realized by an incredibly small, fleeting wormhole, acting as a subtle, subatomic bridge between them. This geometric connection would not allow for any physical object or information to pass through, but it would provide the underlying space-time structure that facilitates the mysterious entanglement. It's a serene and elegant way to visualize the non-local nature of quantum entanglement, offering a gravitational explanation for a phenomenon that has long puzzled physicists. This theoretical linkage suggests that the universe's fundamental connections might be far more intricate and geometrically rich than previously imagined, with subtle, hidden pathways facilitating quantum correlations. The quiet elegance of this proposal lies in its potential to unify disparate concepts, revealing a deeper, more cohesive understanding of reality's delicate threads. This placid connection between quantum particles and space-time geometry offers a profound new perspective on the universe's fundamental architecture. This intriguing concept, the ER-EPR conjecture, is still highly speculative and remains under active research within the realm of theoretical physics. While it offers an elegant and compelling way to link two fundamental mysteries of the universe, wormholes and quantum entanglement, it is far from an established scientific fact. Scientists are diligently exploring its mathematical implications, debating its consistency with known physics, and seeking potential avenues for conceptual or experimental verification. However challenging that may be, the conjecture pushes the boundaries of our current understanding, inviting physicists to develop new theoretical frameworks that can reconcile general relativity with quantum mechanics. It is a vibrant frontier of intellectual inquiry, where brilliant minds calmly grapple with the universe's most profound questions, patiently piecing together the subtle connections that define reality. This active exploration underscores the dynamic nature of scientific discovery, where even the most audacious ideas are rigorously examined. The serene pursuit of understanding, even when faced with deep unknowns, continues to enrich our cosmic contemplation, revealing the boundless capacity of human curiosity to explore the universe's most intricate and enigmatic secrets. This ongoing journey of discovery, even with its speculative elements, provides a placid and continuous unfolding of cosmic knowledge. As we delve deeper into the theoretical conditions necessary for wormholes, we encounter certain profound challenges that emerge from the very foundations of general relativity. Within the intricate tapestry of general relativity, a series of profound theoretical declarations, known as no-go theorems, gently suggest that the creation and sustained existence of traversable wormholes present formidable challenges. These theorems are not absolute prohibitions, but rather elegant mathematical pronouncements, acting as subtle cosmic warnings that the universe, in its serene wisdom, places significant hurdles before such extreme manipulations of space-time. They emerge from the deepest computations of gravitational theory, patiently revealing the inherent resistance of the cosmic fabric to remaining open in such an unnatural configuration. These theoretical barriers indicate that the universe's fundamental laws, while allowing for the concept, make its practical realization exceptionally difficult, demanding conditions that are far from ordinary and perhaps beyond our grasp. The quiet authority of these theorems guides our understanding, suggesting that such cosmic shortcuts are not easily woven into the fabric of reality, underscoring the delicate balance required for sustained gravitational structures. The serene contemplation of these theoretical limitations reminds us of the profound complexity inherent in bending spacetime to our will, offering a placid acknowledgement of the universe's unyielding principles. This gentle resistance from the cosmos itself teaches us patience and precision in our theoretical explorations, allowing for a deeper appreciation of the subtle dance between possibility and constraint. These profound no-go theorems often relate directly to the violation of fundamental energy conditions, which are cornerstone assumptions in our understanding of how matter and energy interact with gravity. The theorems essentially demonstrate that for a wormhole to remain open and traversable, the material holding it open must possess properties that contradict these widely accepted energy conditions. This connection is vital, as it links the abstract mathematical difficulties of wormhole stability to the very nature of the matter and energy that would be required to create them. It implies that the universe, as we generally perceive it, does not readily provide the ingredients for such cosmic passages. The subtle interplay between space-time geometry and matter's characteristics is at the heart of this theoretical dilemma. These theorems, therefore, serve as a calm and clear indication that the existence of traversable wormholes demands a departure from our conventional understanding of cosmic substances, inviting us to explore the edges of physical possibility. This quiet revelation about the universe's fundamental rules guides our search for extraordinary solutions, patiently unveiling elegant link between these theorems and energy conditions, underscores the deeply intertwined nature of gravity and matter, urging a profound reconsideration of their interplay. To fully grasp the significance of these violations, it is helpful to understand what these energy conditions entail. Energy conditions are fundamental assumptions about the nature of matter and energy, typically stating, in their simplest form, that energy density is positive. This means that any form of matter or energy, from the tiniest photon to the grandest galaxy, contributes a positive amount to the total energy content of space-time. In our everyday experience, and across the vast observable universe, this holds true. Mass has positive energy, and all known forms of energy, such as light or kinetic energy, are positive. These conditions are deeply embedded in our cosmological models, forming the stable bedrock upon which our understanding of gravity and cosmic evolution rests. They represent the normal behavior of the universe, ensuring that gravity remains an attractive force and that space-time generally behaves in a predictable, stable manner. The placid acceptance of these conditions allows us to construct coherent models of the cosmos, providing a serene framework for understanding its gentle, yet powerful, dynamics. This quiet affirmation of positive energy density is a subtle, pervasive truth that shapes the very fabric of our reality, guiding our contemplation of the universe's fundamental characteristics. It is precisely here that the concept of exotic matter, with its extraordinary negative energy density, fundamentally violates these established energy conditions. While ordinary matter and energy create a positive curvature in spacetime, leading to gravitational attraction, exotic matter would, in theory, generate a negative curvature. This means it would effectively possess less than zero energy, or a repulsive form of energy that pushes spacetime outward instead of drawing it inward. This property is profoundly counterintuitive, challenging our most basic understanding of what energy is and how it behaves. The violation of these energy conditions is not a minor deviation. It is a radical departure from the norm, a theoretical necessity for wormhole stability that pushes the boundaries of conventional physics. It is the serene defiance of these fundamental assumptions that allows exotic matter to act as the cosmic scaffolding, holding open the wormhole's throat against the natural tendency for gravity to collapse it. The quiet elegance of this violation is what makes traversable wormholes such a captivating, yet challenging subject of theoretical inquiry. This profound departure from the usual cosmic rules invites us to reconsider the universe's deeper, more subtle possibilities, patiently exploring the intricate interplay between the known and the unknown. Without the precise and sustained violation of these energy conditions, the theoretical wormholes would either be non-traversable, much like the original Einstein-Rosen bridges that snap shut instantly, or they would collapse at the unyielding speed of light. Imagine the universe's fabric, left to its own devices under the influence of ordinary gravity. Any extreme curvature, such as that forming a wormhole, would naturally seek to flatten out or pinch off, much like a bubble popping. The energy conditions are essentially a statement that this is the natural, stable outcome for spacetime in the presence of positive energy. Therefore, if these conditions are not violated by the presence of exotic matter, the wormhole simply cannot remain open. It would either close too quickly for anything to pass through, or it would never achieve a stable, open configuration in the first place. This stark reality underscores the absolute necessity of exotic matter with its negative energy density for the very concept of a stable, traversable wormhole to hold any physical possibility. It is a serene, yet firm, declaration by the universe that shortcuts through space-time demand extraordinary, non-conventional physical properties. This quiet necessity patiently reveals the profound and intricate requirements for any enduring cosmic pathway, guiding our understanding toward the universe's subtle yet powerful constraints. Consequently, the very existence of traversable wormholes ultimately depends on whether these energy conditions can be circumvented in reality, either through the natural occurrence of exotic matter or by some as yet undiscovered mechanism that allows for localized negative energy densities. This is the central, profound question that theoretical physicists calmly grapple with. Can the universe, in its boundless complexity, provide the subtle means to defy these widely accepted energy conditions on a macroscopic scale? Or are these conditions truly inviolable, making traversable wormholes forever confined to the realm of elegant mathematical abstraction? The answer to this question holds the key to whether wormholes are merely fascinating theoretical constructs, or whether they represent a genuine, albeit challenging, possibility for cosmic travel and temporal manipulation. Understanding the universe's deepest laws intersects with the most ambitious dreams of interstellar exploration. The quiet contemplation of this fundamental dependency guides our research, patiently seeking to uncover the subtle ways in which the universe might allow for such extraordinary phenomena, transforming our understanding of its fundamental fabric. This profound dependence on the circumvention of energy conditions remains a major theoretical hurdle for their physical realization. It is not a trivial problem that can be easily overcome with minor adjustments to our theories. Instead, it strikes at the heart of our fundamental understanding of matter, energy, and gravity. The need for exotic matter with negative energy density represents a significant departure from all known physics. While the Casimir effect offers a tantalizing hint of negative energy on microscopic scales, scaling that up to hold open a wormhole large enough for a spacecraft would require an immense leap in our understanding and control of quantum phenomena. Until such a substance is either discovered in nature or theoretically shown to be manufacturable in sufficient quantities, traversable wormholes will continue to exist primarily in the realm of scientific speculation and captivating science fiction. This formidable obstacle serves as a serene reminder of the universe's deep complexities, patiently awaiting a breakthrough that could reshape our understanding of what is truly possible within its vast and silent embrace. The quiet elegance of this theoretical challenge inspires continued intellectual exploration, appreciation of the universe's most profound limits and hidden potentials. It is perhaps in the realm of human imagination, particularly within science fiction, that wormholes truly flourish, becoming a profoundly popular staple for both interstellar travel and the intriguing concept of time travel. In countless narratives, from serene novels to captivating cinematic adventures, these theoretical cosmic tunnels serve as an elegant solution to the otherwise insurmountable distances and temporal barriers that define our universe. They offer a graceful bypass, a narrative device that allows storytellers to transport characters across vast cosmic gulfs or through different epochs, without the arduous, often prohibitive, constraints of conventional physics. This widespread popularity reflects a deep human desire to transcend the limitations of space and time, to explore the universe with a sense of boundless freedom and ease. The mere thought of such effortless cosmic transit brings a quiet sense of wonder, allowing for transforming the daunting immensity of space into a network of accessible pathways. Within these imaginative tales, wormholes represent not just a scientific concept, but a symbol of hope and limitless possibility, inviting audiences to dream of a cosmos that is intimately interconnected and endlessly explorable, a tranquil tapestry woven with threads of distant stars and future moments. A particularly evocative example of this depiction can be found in films like Interstellar, where wormholes are portrayed as stable, almost placid pathways for incredibly long-distance journeys. In such cinematic visions, the wormhole is often presented as a grand, ethereal sphere or a luminous tunnel, a calm gateway, allowing spacecraft to drift serenely from one galactic arm to another, bypassing light years of empty space. The narrative often sidesteps the immense theoretical challenges, such as the need for vast quantities of exotic matter, in favor of focusing on the journey itself and its profound implications. These cinematic wormholes function as reliable conduits, offering a tranquil and efficient method for characters to reach distant star systems, fostering a sense of immediate connection between disparate parts of the cosmos. This artistic interpretation serves to solidify the image of a wormhole as a functional, even majestic, piece of cosmic infrastructure, a silent, enduring bridge that allows for the graceful unfolding of cosmic narratives. The peaceful passage through these depicted wormholes invites a profound sense of awe, transforming the terrifying unknown into a navigable wonder, a testament to the power of imagination to render the most complex scientific theories into beautifully accessible experiences, guiding us toward a serene acceptance of theoretical possibilities. Crucially, the very concept of a wormhole elegantly allows for circumventing the speed of light limit for effective travel between distant points, not by breaking this fundamental cosmic speed barrier, but by bending spacetime itself. When we speak of circumventing the speed of light, it is important to clarify that an object traversing a wormhole would still move at a speed less than or equal to the speed of light through the wormhole's throat. However, because the wormhole effectively shortens the distance between two incredibly distant points in normal space, the effective speed of travel, from the perspective of an external observer, would appear to be much faster than light. Imagine folding a vast cosmic map. The wormhole punches a hole through the fold, allowing a direct, short journey instead of a long one across the flat surface. This theoretical shortcut offers a profound solution to the immense challenge of interstellar travel, which is otherwise limited by the light speed barrier, rendering journeys between stars impossibly long. The serene promise of such effective superluminal travel is what makes wormholes so captivating, offering a tranquil means to explore the vastness of the universe without the crushing burden of multi-millennia voyages. This subtle, yet powerful manipulation of spacetime's geometry allows for a calm and unhurried passage across what would otherwise be an insurmountable cosmic gulf, patiently revealing the universe's potential for elegant shortcuts. Beyond their function as mere conduits, wormholes gracefully offer a powerful narrative device for exploring vast cosmic distances and venturing into different eras of time. In storytelling, their existence liberates characters from the strictures of conventional travel, allowing for dynamic plots that span multiple star systems or even millennia. A single journey through a wormhole could transport protagonists to a newly discovered exoplanet in a distant galaxy, offering opportunities for encountering diverse alien life or uncovering ancient cosmic mysteries. Alternatively, if configured for time travel, a wormhole could provide a serene passage to the distant past, allowing for quiet observation of historical events, or a glimpse into the far future, revealing the ultimate fate of civilizations or stars. This versatility makes them an invaluable tool for writers seeking to expand the scope of their narratives, enabling the exploration of themes related to cosmic scale, temporal causality, and the fundamental nature of reality itself. The placid flow of such narratives, unburdened by the usual constraints of distance and time, allows for a deeper, more contemplative engagement with the universe's grand story, revealing its subtle complexities and boundless wonders. This gentle narrative freedom inspires a sense of limitless exploration, guiding our imagination through the universe's endless possibilities. Venturing into the more speculative realms of theoretical physics, some intriguing ideas suggest that wormholes might connect not just distant points within our own universe, but potentially to parallel universes or even different branes in string theory. The concept of parallel universes posits the existence of other realities, separate yet coexisting with our own, each with its unique set of physical laws, histories, or outcomes. A wormhole, in this highly speculative context, could serve as a delicate cosmic portal, a serene gateway from our reality to another, allowing for an exploration of entirely different cosmic landscapes. Furthermore, in string theory, a leading candidate for a theory of quantum gravity, the universe might be envisioned as a brane, a higher dimensional membrane floating within a larger, unseen bulk space. Wormholes, in this framework, could potentially offer connections between different branes, perhaps even linking our own three-dimensional universe to other, hidden dimensions, or parallel brane universes. These are concepts that push the very edge of theoretical understanding, inviting physicists to ponder the universe's fundamental architecture in ways that transcend our current observational capabilities. This serene speculation offers a placid glimpse into the universe's deepest, most enigmatic structures, revealing a potential tapestry of realities woven together by unseen threads. Should such profound connections indeed exist, these wormholes, linking to parallel universes or different branes, would open up truly astonishing possibilities for exploring entirely different realities. Imagine stepping through a wormhole not just to another galaxy, but into a cosmos where the laws of physics are subtly altered, where gravity behaves differently, or where the fundamental constants of nature have unique values. This would present an opportunity for unprecedented scientific discovery, allowing researchers to test the robustness of our physical laws against alternative cosmic backdrops. Furthermore, it could reveal completely new forms of life, different evolutionary pathways, or even alternative histories for intelligent civilizations. The implications for philosophy, for our understanding of existence and identity, would be immense. It's a serene vision of boundless exploration, a tranquil journey into the infinite variations of cosmic possibility, where every passage through a wormhole could unveil a universe unlike our own. This profound potential for discovery invites a calm and unhurried contemplation of the universe's ultimate diversity, patiently expanding the horizons of our cosmic awareness. The gentle unveiling of different realities offers a deep sense of wonder and intellectual liberation, challenging our most fundamental assumptions about the unique nature of our own existence. It is important to acknowledge, with a calm and reflective tone, that all these captivating ideas, particularly those concerning wormholes as time machines or gateways to other realities, remain firmly in the realm of theoretical physics and philosophical inquiry. While mathematically consistent within certain frameworks, they lack any form of empirical evidence or observational confirmation. Scientists continue to explore these concepts with rigorous mathematical models and thought experiments, pushing the boundaries of what is conceivable within the laws of physics. However, without concrete data or experimental verification, they remain elegant possibilities rather than established facts. This persistent speculative status invites a deeper, more nuanced form of contemplation, where the mind is free to wander through the cosmos's most enigmatic potentials without the constraints of immediate proof. The philosophical implications alone are profound, forcing us to consider the nature of reality, causality, and the very structure of existence. This serene intellectual journey into the unknown underscores humanity's enduring quest for understanding, patiently expanding our grasp of the universe's most profound and subtle secrets. The quiet pursuit of these theoretical wonders continues to enrich our cosmic contemplation, offering a placid space for imagination to soar amidst the vast, silent expanse. To gain a truly complete and comprehensive understanding of wormholes, particularly their intricate internal mechanics and the profound stability requirements, scientists believe we will likely require nothing less than a fully developed and unified theory of quantum gravity. Our current frameworks, while powerful and remarkably successful in their respective domains, encounter fundamental limits when confronted with the extreme conditions that wormholes, by their very nature, represent. It is at these conceptual boundaries of knowledge, where the very fabric of space-time is stretched and bent to its utmost, that the serene need for a more encompassing perspective becomes profoundly apparent, gently pushing the frontiers of cosmic comprehension into new and uncharted territories. This quiet realization underscores the delicate balance between our present understanding and the vast expanse of what remains to be discovered, patiently guiding our intellectual journey. General relativity, a masterpiece of modern physics, beautifully describes the subtle dance of gravity on vast cosmic scales. From the elegant orbital ballet of planets around their stars to the majestic, unhurried evolution of entire galaxies. Its predictions, concerning everything from the bending of starlight by massive objects to the gentle expansion of the universe, have been confirmed with exquisite precision, painting a serene and remarkably accurate picture of the large-scale universe we inhabit. However, this profoundly elegant theory, for all its triumphs and enduring beauty, gracefully breaks down at the incredibly tiny, intensely energetic quantum scales. When confronting phenomena like the heart of a black hole, where matter is compressed to infinite density, or the universe's very first moments after the Big Bang, where all of reality was minuscule and energetic beyond measure, general relativity's equations no longer provide coherent or reliable answers. This quiet limitation highlights the inherent need for a deeper understanding, a more encompassing and subtle framework that can reconcile the macroscopic with the microscopic, particularly within the extreme curvatures and profound densities that would define a wormhole's delicate throat. It is in these ultimate extremes that our current models reach their serene boundaries, inviting a new era of theoretical exploration. It is into this profound theoretical void that quantum gravity theories gently step, offering new and transformative insights into the universe's most fundamental workings. Prominent among these ambitious conceptual frameworks are fascinating ideas such as string theory and loop quantum gravity. String theory, with its elegant premise, envisions all fundamental particles not as infinitesimal points, but rather as tiny, vibrating one-dimensional strings, existing within a tapestry of 10 or 11 dimensions, far beyond our immediate perception. Loop quantum gravity, on the other hand, attempts to quantize space-time itself, proposing a granular, atomic-like structure for space and time at the smallest scales, where space-time is woven from discrete loops or atoms of gravity. These ambitious theories, each with its unique approach, strive to unify the elegant principles of general relativity, which governs the very large, with the enigmatic rules of quantum mechanics, which dictate the behavior of the very small. Their goal is to create a single, harmonious description of all fundamental forces, offering a serene and comprehensive understanding that can describe the universe from its grandest structures to its most infinitesimal components, potentially resolving some of physics' deepest and most enduring mysteries. This placid quest for unification represents humanity's patient search for the ultimate cosmic narrative, a gentle unfolding of reality's deepest secrets. With such advanced theoretical frameworks at our disposal, scientists calmly hope to potentially describe the serene yet extreme behavior of spacetime at the intense curvatures found within a wormhole. General relativity, as we noted, struggles profoundly with these regions of immense gravitational distortion, often predicting singularities, points of infinite density and curvature where its equations lose all meaning and predictive power. A successful and coherent theory of quantum gravity, however, could offer a coherent, non-singular description of the wormhole's intricate throat, portraying it not as an impossible point of infinity, but as a region of highly granular, yet finite and describable, spacetime. This would allow for a more complete, stable, and physically plausible understanding of how matter and energy would interact within such a cosmic conduit, making the concept of safe passage through a wormhole more theoretically viable. The ability to model these extreme environments with subtle precision is absolutely crucial for moving wormholes from the realm of pure speculation to a more grounded theoretical possibility, quietly unveiling the universe's most intricate and profound gravitational dynamics. This deeper insight would provide a tranquil, clearer picture of what truly happens at the heart of these cosmic shortcuts. Furthermore, these nascent quantum gravity theories might also provide natural mechanisms for the subtle existence, or even the stabilization of the mysterious exotic matter. As we discussed earlier, is a theoretical requirement for holding a wormhole open, yet it is profoundly absent in our everyday experience and largely unexplained by conventional physics. Current physics struggles to explain how such a substance could naturally arise or be sustained in sufficient quantities within the observable universe. Quantum gravity, by offering a deeper understanding of the vacuum itself, of fundamental quantum fields, and of the nature of energy at its most basic and subtle level, could potentially predict or allow for the gentle creation or manipulation of such negative energy states. This would be a game-changing revelation, transforming the theoretical requirement for exotic matter from a major, seemingly insurmountable hurdle into a natural consequence of a more complete and elegant physical law. It offers a placid vision of the universe, providing its own solutions, patiently revealing the subtle ways in which its fundamental forces might conspire to create these extraordinary shortcuts, making the seemingly impossible theoretically feasible within a grander, more unified framework. This quiet potential provides a serene impetus for further exploration. It becomes serenely clear that the intricate interplay between quantum mechanics, which so elegantly describes the universe at its smallest, most fundamental scales, and general relativity, which gracefully governs the grand architecture of spacetime, is absolutely crucial for solving the profound mysteries surrounding wormholes. Neither theory alone, in its current form, possesses the full explanatory power needed to fully comprehend these enigmatic and extreme structures. Wormholes are, in essence, a macroscopic phenomenon, a large-scale curvature of spacetime that demands quantum-level properties, such as exotic matter, for their stability and traversability. This precise convergence of the very large and the very small, of the cosmic and the subatomic, is precisely what makes wormholes such a challenging and endlessly fascinating subject for scientific inquiry. A truly unified framework, capable of seamlessly integrating both quantum mechanics and general relativity, is essential to understand how these disparate realms merge to create such extreme gravitational geometries, gently bridging the conceptual gap between two powerful, yet ultimately incomplete, descriptions of reality. This serene synthesis of cosmic and quantum understanding offers a placid path toward unraveling the universe's deepest secrets, patiently revealing the intricate web of its fundamental laws and connections. In this profound sense, wormholes consistently push the very boundaries of our current physical understanding, gently inviting the development of entirely new theoretical frameworks. They act as intellectual signposts, silently pointing towards the limitations of our existing models and urging scientists to transcend them with fresh perspectives. The persistent questions surrounding wormholes, their potential existence, their stability, their implications for interstellar travel, and their mind-bending connection to time travel compel physicists to calmly rethink fundamental assumptions about space, time, matter, and energy. This relentless and inspiring challenge spurs brilliant minds to forge novel concepts, to devise innovative mathematical tools, and to envision the universe in ways previously unimagined. It is a quiet testament to the dynamic and ever-evolving nature of scientific progress, where profound mysteries serve as catalysts for intellectual evolution, guiding us toward a more complete and coherent picture of the cosmos. The serene pursuit of these elusive phenomena ensures that the frontiers of physics remain vibrant and endlessly captivating, patiently revealing the universe's boundless capacity for wonder and intellectual growth, always pushing the limits of what we can know. As we contemplate the profound theoretical potential of traversable wormholes, a crucial aspect to consider, especially for any potential cosmic voyagers, involves the delicate conditions required for safe passage. For a human being to safely traverse a wormhole, the subtle yet powerful gravitational stresses known as tidal forces, both at its ethereal mouth and deep within its winding throat, would need to be exquisitely gentle. These forces arise from the differential pull of gravity across a body, meaning that one part of a traveler's form might experience a slightly stronger gravitational tug than another. In the context of a wormhole, this difference in gravitational intensity, if too pronounced, could become devastating. Therefore, an ideal wormhole for human transit would need to be designed, or perhaps naturally formed, in such a way that these gravitational disparities are minimized to an almost imperceptible level. The journey must be one of placid uniformity, where the gravitational embrace is so soft and even that a traveler would feel no undue strain or distortion. This requirement for extreme gentleness underscores the immense theoretical hurdles involved in crafting a truly hospitable cosmic shortcut, patiently revealing the universe's subtle demands for delicate manipulation of its deepest gravitational contours. The serene dream of human interstellar travel through such a conduit hinges entirely upon this quiet, yet absolute condition of gravitational equilibrium, ensuring a tranquil and unhurried passage through the fabric of space and time. This intricate balance speaks to the profound elegance of cosmic design, even in its hypothetical form, inviting contemplation into the precise engineering of spacetime itself for the comfort and safety of a delicate organic voyager. Should these crucial conditions for gentle tidal forces not be met, a traveler attempting passage through a wormhole would face a truly profound and unsettling fate. Strong tidal forces would inexorably stretch a voyager to a thin, elongated strand, a process famously and calmly described as spaghettification. Imagine a body, whether human or spacecraft, entering a region where the gravitational pull on its feet is many times stronger than the pull on its head. This immense differential in force would cause the object to be drawn out, attenuated, and pulled apart along the direction of the gravitational gradient, much like a piece of dough being gently, yet relentlessly, stretched to an extreme thinness. It is not a violent tearing, but a serene, inevitable elongation caused by the sheer, overwhelming power of gravity acting unevenly across a form. This quiet, almost imperceptible stretching would continue until the object's molecular bonds could no longer withstand the strain, leading to a complete disintegration. The prospect of spaghettification highlights the raw, unyielding power of extreme gravity and the delicate fragility of biological or even engineered structures when confronted with such profound cosmic forces. It is a tranquil, yet stark reminder of the universe's inherent dangers, patiently revealing the severe consequences of venturing into space-time regions without adequate protection from its most potent gravitational influences. The serene elegance of this process, though devastating, speaks to the universe's impartial adherence to its fundamental laws, painting a vivid picture of cosmic transformation. This process of spaghettification, the stretching of an object into a thin strand by overwhelming tidal forces, is strikingly similar to what is theoretically believed to happen near a black hole's event horizon. When an object crosses the point of no return around a black hole, it encounters gravitational gradients so steep and intense that the differential forces inevitably cause it to be elongated and torn apart before reaching the central singularity. The physics governing this stretching phenomenon are fundamentally the same, whether near a black hole or at the mouth of an unstable wormhole. Both scenarios involve space-time being curved to an extreme degree, creating immense disparities in gravitational pull across a finite distance. This parallel underscores the extreme conditions that even a theoretical wormhole must overcome to be considered traversable. It is a serene connection between two of the cosmos's most enigmatic theoretical constructs, revealing how the same fundamental laws of gravity dictate the fate of matter in regions of ultimate curvature. The quiet elegance of this shared gravitational effect offers a deeper, unified understanding of the universe's most extreme environments, patiently linking the conceptual dangers of black holes with the challenges of wormhole navigation, providing a calm, consistent narrative of cosmic perils. To avoid such a perilous fate, a wormhole large enough to prevent spaghettification would require an almost incomprehensibly immense amount of exotic matter. The wider the wormhole's throat, the more spread out the gravitational curvature becomes, leading to gentler tidal forces. However, holding open such a vast expanse of space-time against its natural tendency to collapse demands an extraordinary quantity of the elusive exotic matter with its negative energy density. Imagine the sheer scale of energy required to prop open a cosmic tunnel that could span light years. Maintaining an opening wide enough for an entire starship to pass through without experiencing destructive tidal effects. This requirement pushes the boundaries of what is theoretically plausible, far beyond the tiny fleeting instances of negative energy observed in laboratory settings. The colossal volume of exotic matter needed would be equivalent to the mass of many stars, or even entire galaxies, a scale that seems almost impossible to gather or sustain. This immense requirement presents a profound, serene hurdle to the physical realization of traversable wormholes, suggesting that while mathematically conceived, their practical construction or natural occurrence might be exceptionally rare, if not entirely impossible. The quiet grandeur of this theoretical demand emphasizes the profound energies needed to sculpt the universe's fabric, patiently revealing the true cost of bending space-time to our will. Therefore, the size of the wormhole's opening is not merely a matter of convenience, but is critically important for human survival during passage. A narrow wormhole, even if theoretically stable, would still exert devastating tidal forces on any macroscopic object attempting to pass through, inevitably leading to spaghettification. For a human or a spacecraft to pass safely, the diameter of the wormhole's throat would need to be vast, perhaps many kilometers or even hundreds of kilometers wide. This immense scale would ensure that the gravitational field across the traveler's body remains nearly uniform, preventing the dangerous differential pulls. Imagine a serene, cavernous tunnel, so wide that the curvature of space-time within it is almost imperceptible, allowing for a smooth and unhurried drift. This requirement for a substantial opening transforms the theoretical wormhole from a mere pinprick in space-time into a grand, majestic gateway, demanding an equally grand amount of stabilizing exotic matter. The quiet elegance of this scale requirement emphasizes the intricate relationship between safety, size, and the subtle manipulation of cosmic forces, patiently revealing the universe's precise demands for any form of safe cosmic transit. Moreover, even if a traversable wormhole could be successfully stabilized and its tidal forces rendered gentle enough for safe passage, the conditions inside its ethereal throat might still prove profoundly hostile to life. Beyond the immediate danger of stretching, a wormhole's interior could present a myriad of other environmental challenges. Consider the potential for intense radiation, perhaps residual energy from the exotic matter itself, or from cosmic rays concentrated by the wormhole's gravitational fields. Extreme temperature gradients, fluctuating from incredibly cold to searingly hot, could also pervade the passage. The vacuum of space would certainly be present, requiring advanced life support systems, but the nature of that vacuum could be unique and unforgiving. There might be unknown forms of energy or particle fluxes that are inimical to organic life. The very act of manipulating spacetime to create such a conduit could lead to unforeseen physical phenomena within its confines. It's a serene reminder that even the most elegant theoretical solutions can harbor hidden complexities and dangers, inviting a cautious and thorough contemplation of the complete environment. The quiet uncertainty of these internal conditions underscores the profound challenges in transforming a theoretical pathway into a truly hospitable cosmic route, patiently revealing the universe's subtle, yet potent, environmental demands. Indeed, the precise environment within the wormhole's throat remains a subject of intense and ongoing theoretical modeling. Since no wormholes have ever been observed, and exotic matter remains largely hypothetical, scientists must rely on complex mathematical simulations and theoretical extrapolations to predict what conditions a traveler might encounter. These models explore various scenarios, considering different distributions of exotic matter, different gravitational configurations, and the potential interplay with quantum effects. The goal is to paint a clearer picture of the internal physics, to understand everything from the gravitational stresses and energy fields to the potential for radiation or other exotic phenomena. It is a painstaking and intricate process, requiring the most advanced computational and theoretical tools. This quiet dedication to modeling the unseen underscores humanity's profound scientific curiosity, patiently attempting to illuminate the darkest corners of theoretical possibility. The serene pursuit of this detailed understanding ensures that our contemplation of wormholes is grounded in the most rigorous theoretical physics available, pushing the boundaries of what we can imagine and calculate about the universe's most enigmatic structures. This continuous theoretical exploration offers a placid and thoughtful approach to understanding the universe's profound yet hidden pathways. Moving from the theoretical existence of wormholes to their potential creation, we encounter a challenge of truly cosmic proportions. Creating or manipulating a wormhole would demand an extraordinarily advanced understanding and an unprecedented level of control over space-time itself. It is not merely a matter of building a machine, but of sculpting the very fabric of reality, bending its geometry with deliberate precision. Imagine the universe's space-time as a vast, supple sheet. To form a wormhole, one would need to delicately, yet powerfully pinch, stretch, and fuse distant parts of this sheet, holding them open against the universe's natural tendencies. This requires a profound mastery of gravitational physics, extending far beyond our current capabilities to merely observe and measure. It would necessitate the ability to precisely dictate how mass and energy influence the curvature of spacetime, to guide its ripples and folds with an almost artistic grace, ensuring stability and safety for any potential passage. Such an endeavor would represent a serene act of cosmic engineering, a testament to an intellect that has fully deciphered and learned to gently command the fundamental architecture of existence, patiently transforming theoretical elegance into tangible cosmic utility. The subtle art of manipulating spacetime itself would be a dance of profound cosmic understanding. Regrettably, this profound level of technology, this capacity to command and reshape the universe's fundamental fabric, is far beyond humanity's current capabilities. Our most advanced endeavors in space exploration, such as sending probes to distant planets or launching powerful telescopes to peer into the cosmic past, represent but the earliest, most delicate steps in understanding the vastness around us. The leap from these achievements to actively creating and stabilizing a wormhole is akin to comparing a simple stone tool to an intricate supercomputer. We lack not only the immense energy sources required, but also the fundamental theoretical and practical knowledge to even begin to manipulate spacetime in such a sophisticated manner. Our current understanding of quantum gravity, which would be essential for such a feat, is still in its nascent stages. Therefore, while the concept of wormholes inspires our dreams, the practical means to bring them into being remain firmly in the realm of distant, futuristic aspiration, patiently awaiting centuries, perhaps millennia, of scientific and technological advancement. The tranquil recognition of this immense technological gap fosters a gentle humility, reminding us of our place in the grand, unhurried timeline of cosmic progress, quietly acknowledging the universe's profound secrets yet to be unveiled. To truly envision a civilization capable of such a monumental achievement, we must look to the most advanced theoretical constructs of cosmic development, such as the Kardashev scale. On this scale, a Type 3 civilization might theoretically possess the immense power and sophisticated understanding necessary to manipulate spacetime and create wormholes. A Type 1 civilization can harness all the energy available on its home planet. A Type 2 civilization can harness the total energy output of its star, perhaps through a colossal structure like a Dyson sphere. A Type 3 civilization, however, represents a truly galactic-scale entity, capable of harnessing the entire energy output of its home galaxy. This colossal energy potential, combined with a mastery of fundamental physics, would provide the theoretical means to gather and control the vast amounts of exotic matter and energy required for wormhole construction. Such a civilization would have patiently evolved over billions of years, achieving a serene command over cosmic forces that is almost unimaginable to us. The very thought of such an advanced entity silently weaving wormholes into the cosmic tapestry evokes a profound sense of wonder and the boundless potential of intelligence across the universe. Their gentle, almost imperceptible manipulation of spacetime would be a testament to a deep, integrated understanding of cosmic mechanics, offering a placid vision of ultimate technological prowess. Indeed, such a Type 3 civilization would not merely need a theoretical understanding. They would need to actively harness immense amounts of energy and, crucially, vast quantities of exotic matter. The energy required to generate the extreme spacetime curvatures that define a wormhole and then to sustain them would be on a galactic scale, potentially equivalent to the output of billions of stars. This is not simply about powering a spacecraft, but about actively reshaping the universe itself. Furthermore, the persistent need for exotic matter with its elusive negative energy density remains a central challenge. This civilization would either need to discover abundant natural sources of such matter or possess the unparalleled ability to create and stabilize it in colossal quantities. Imagine a serene and meticulous process of collecting or synthesizing this rarest of substances, then carefully distributing it to prop open a cosmic passage against the overwhelming gravitational tendency to collapse. This dual requirement, immense energy and unprecedented control over exotic matter, underscores the profound difficulty of wormhole creation. Even for the most advanced theoretical civilizations, it speaks to a level of cosmic engineering that transcends our current comprehension, a quiet testament to the universe's subtle yet powerful demands for such profound interventions. The ability to engineer spacetime, to precisely manipulate its curvature and topology, would open up truly revolutionary possibilities, extending far beyond merely creating shortcuts for travel. Imagine the capacity to reshape local gravitational fields, perhaps to create artificial gravity environments in space, or to even subtly alter the flow of time within a confined region. Such mastery could allow for the construction of entirely new, stable regions of spacetime, perhaps creating cosmic habitats tailored to specific needs, or even for generating new forms of energy derived from spacetime itself. The universe would no longer be a static backdrop, but a dynamic medium, pliable to the will of an advanced intelligence. This profound capability would revolutionize not only travel, but also energy generation, material science, and our very understanding of reality. It would transform the cosmic landscape into a canvas for grand, serene creations, allowing for an unhurried, deliberate shaping of the universe's fundamental dimensions. The gentle power to sculpt space-time offers a placid vision of limitless innovation, patiently revealing the profound creative potential inherent in a deep understanding of cosmic laws. Such an achievement would undoubtedly represent a profound leap in our command over the fundamental forces of the universe. Gravity, one of the four fundamental forces, is the most pervasive and, arguably, the least understood in terms of direct manipulation. While we have learned to harness electromagnetism for electricity and communications, and nuclear forces for energy, gravity remains largely beyond our direct influence. The ability to create and control a wormhole would signify a complete and total mastery over gravity, moving beyond mere observation or passive utilization. It would imply a deep, integrated understanding of how gravity interacts with matter and energy at its most fundamental levels, perhaps even resolving the elusive quest for a unified theory of everything. This command would signify a profound evolutionary step for any civilization, transforming them into true architects of the cosmos, capable of shaping the universe in ways that were once considered the exclusive domain of natural processes. It is a serene vision of ultimate scientific and technological triumph, a quiet testament to the boundless capacity of intelligent life to unravel and harness the universe's deepest secrets, patiently revealing the majestic heights of cosmic wisdom. Unsurprisingly, this awe-inspiring concept inspires futuristic visions of grand cosmic infrastructure, transforming the universe from a collection of isolated islands into a truly interconnected network. Imagine a sprawling tapestry of wormholes, strategically placed throughout a galaxy, functioning as cosmic expressways or intergalactic transit hubs. Civilizations could effortlessly connect distant star systems, allowing for swift trade, rapid communication, and the peaceful exchange of knowledge and cultures across immense distances. Planets could be linked to their colonies in other star clusters, fostering a sense of galactic community. This infrastructure would not only facilitate travel, but would fundamentally alter the dynamics of cosmic society, enabling a seamless flow of life and ideas across the universe. The very notion of such a tranquil and efficient network paints a serene picture of a future where the vastness of space is no longer a barrier, but a navigable expanse, carefully designed for the gentle exploration and harmonious coexistence of countless civilizations. This quiet dream of cosmic connectivity, where wormholes serve as the elegant threads weaving together the universe, provides a placid and enduring inspiration for humanity's future among the stars, patiently revealing the profound beauty of an intricately connected cosmos. Yet, for these theoretical wonders to transition from elegant mathematical constructs to observable realities, we must consider how we might find them. If wormholes truly exist, their presence would not likely be announced with dramatic flares or overt signals, but rather through the subtle, almost imperceptible ways they interact with the light traversing the universe, a gentle whisper across the vast cosmic expanse. Indeed, if these enigmatic tunnels were woven into the very fabric of space-time, their profound gravitational effects would inevitably lead to the subtle distortion of light originating from distant background objects. Imagine the serene journey of photons, particles of light, traveling across billions of light-years from faraway galaxies, only to encounter the intense curvature of space-time around a hidden wormhole. Just as a massive galaxy or a colossal cluster of matter gently bends and subtly magnifies the light from celestial bodies situated behind it, a wormhole would similarly warp the paths of these photons. This phenomenon, known with quiet authority as gravitational lensing, is a well understood and frequently observed consequence of Einstein's general relativity. where the immense presence of mass and energy acts like an immense natural lens, subtly reshaping the cosmic vistas we perceive. A wormhole, with its distinct and extreme geometry, would imprint its own characteristic signature upon the light passing near its ethereal mouth, creating a gentle, yet discernible alteration in the apparent positions, shapes, and even brightness of stars and galaxies observed beyond it. It is a quiet cosmic whisper, a delicate alteration in the luminous tapestry that reaches our sophisticated telescopes, offering a potential clue to its hidden, profound existence. This subtle bending, while often not immediately obvious to the casual observer, holds the key to uncovering these elusive cosmic pathways, allowing the universe itself to gently reveal its most profound and intricate connections through the silent medium of light. The patient observation of these minute deflections becomes a tranquil quest for unseen cosmic architecture, transforming the vast emptiness into a canvas of potential revelation, a placid testament to the universe's subtle power to shape light. Crucially, the gravitational lensing caused by a wormhole would not be identical to the familiar patterns produced by black holes, providing a distinctive and unique fingerprint for potential identification. While both black holes and wormholes are extreme gravitational entities that profoundly bend light, their internal structures and the precise manner in which spacetime is curved around them are fundamentally different. A black hole's lensing typically creates a characteristic ring of light, often referred to as an Einstein ring, or multiple images of a background source, depending on the precise alignment, but always with an opaque central region where light cannot escape, as it is irrevocably drawn into the black hole. A traversable wormhole, however, might produce a more complex and, perhaps most strikingly, a transparent lensing effect. Instead of merely blocking or bending light around an opaque center, a wormhole could theoretically allow light to pass through its throat, potentially showing a profoundly distorted image of the other side of the wormhole, or a magnified and warped view of a completely different region of space altogether, rather than simply blocking it with an event horizon, relative to its true location, already know. This unique optical signature, born from the wormhole's specific open geometry and the theoretical possibility of light passing through its stable throat, offers a serene and elegant way to distinguish it from the more familiar, yet equally profound, lensing effects of black holes. The subtle differences in these cosmic mirages become vital clues, guiding astronomers in their tranquil search for these extraordinary gravitational phenomena, patiently revealing the nuanced beauty of spacetime's diverse and intricate curvatures, each with its own unique visual signature. Therefore, a primary and most promising potential avenue for the detection of wormholes involves the diligent and patient search for these subtle gravitational lensing distortions. Astronomers employ an array of powerful telescopes, both strategically positioned on Earth and gracefully orbiting in space, to meticulously observe distant galaxies, luminous quasars, and other background light sources. Their tranquil quest is to look for any anomalous light patterns, any peculiar arcs, rings, or multiple images of background celestial bodies that cannot be readily explained by the known gravitational effects of visible matter or even dark matter halos. It is a quiet form of cosmic detective work, where minute, almost imperceptible variations in light become profound clues to the universe's hidden structures, much like deciphering an ancient, subtle code embedded in the starlight. By carefully comparing observed lensing events with highly detailed theoretical models of how wormholes would uniquely distort light, scientists patiently sift through vast amounts of complex data, hoping to uncover a distinctive signature that aligns with the precise predictions for these elusive space-time tunnels. This serene and methodical approach relies profoundly on the universe's own light, as a silent, unhurried messenger, carrying potential revelations about its most profound and enigmatic pathways, transforming the routine act of observation into a thoughtful and deeply contemplative exploration of cosmic possibilities. The gentle scrutiny of the heavens for these faint imprints continues, revealing the depth of human ingenuity in the face of cosmic mystery, and the subtle art of cosmic discovery. Despite these sophisticated observational techniques and the tantalizing theoretical possibilities, the sheer immense distances involved in cosmic observations make any detection of wormholes incredibly challenging, a truly daunting task for even the most advanced instruments. The universe is unimaginably vast, with galaxies separated by billions of light years, and the light from these distant sources takes eons to reach us, having journeyed across immense cosmic gulfs. A wormhole, if it exists, could be located anywhere along these immense cosmic pathways, potentially at distances so great that its subtle lensing effects would be almost imperceptible from Earth, blurred by the intervening cosmic dust, gas, and the general gravitational noise of the universe. Furthermore, even if a wormhole were relatively nearby on a galactic scale, its opening might be too small, or its gravitational signature too faint and diffuse, to be resolved with clarity by our current instruments, which, for all their power, have inherent limits. The sheer scale of the cosmos acts as a natural, majestic veil, subtly obscuring many of its most profound and subtle wonders. This quiet reality underscores the immense difficulty of the search, demanding ever more powerful and sensitive telescopes and ever more precise analytical methods to pierce through the cosmic haze. The tranquil patience required for such a cosmic endeavor is immense, a testament to humanity's unwavering commitment to unraveling the universe's most profound secrets, even when faced with the daunting, unhurried scale of its grand and majestic design. The universe's vastness quietly challenges our observational limits, inspiring continuous innovation and a serene, persistent quest for knowledge. In their serene and unhurried exploration of the cosmos, astronomers constantly search for subtle anomalies in the cosmic background that might gently hint at the presence of exotic phenomena, including the elusive wormholes. This tireless vigilance involves scrutinizing vast datasets collected from comprehensive surveys of galaxies. Meticulously detailed cosmic microwave background radiation maps, the ancient afterglow of the Big Bang, and careful observations of distant, luminous quasars. Any unexpected deviation from the precisely predicted distribution of matter or light, any peculiar flicker, subtle distortion, or inexplicable pattern that cannot be readily explained by conventional astrophysical processes, becomes a point of intense, yet calm, scientific investigation. It is akin to finding a single, unusual thread in an immense, exquisitely woven tapestry. A thread that might softly indicate an entirely different, hidden pattern or an underlying cosmic structure previously unimagined. This diligent search extends to looking for minute, almost imperceptible variations in gravitational wave signals, those ripples in spacetime itself, or even subtle effects on the trajectories of high-energy cosmic rays, all of which are potential whispers from the universe's most extreme and enigmatic corners. The quiet persistence of this global effort reflects a deep, abiding scientific curiosity, a patient willingness to consider the unexpected, transforming the routine act of astronomical observation into a profound and deeply thoughtful quest for the universe's deepest, most subtle secrets. This constant vigilance allows for a tranquil openness to discovery, ensuring that no potential cosmic wonder goes unnoticed in the grand, silent expanse, patiently awaiting its moment of revelation. Should a potential wormhole signature ever be observed, whether through the subtle bending of light, the delicate ripples of gravitational waves, or any other as yet undiscovered means, it would immediately require the most rigorous and meticulous verification to calmly rule out all other possible explanations. The universe is teeming with complex, often surprising, and sometimes deceptive astrophysical phenomena, and many observable effects can be mimicked or confounded by conventional objects. For instance, a peculiar lensing pattern that initially seems to suggest a wormhole could potentially be caused by an unusual, yet entirely ordinary configuration of dark matter, or a faint, enigmatic gravitational wave signal might originate from a novel type of stellar collapse or an exotic black hole merger. Therefore, any purported wormhole detection would be subjected to intense, unhurried scrutiny by the global scientific community, demanding independent confirmation from multiple observatories, detailed theoretical modeling to match the observations, and the systematic elimination of all known alternatives. This serene and methodical process of verification is the absolute cornerstone of scientific integrity, ensuring that any profound discovery is robust, reproducible, and beyond all reasonable doubt. It is a quiet testament to the scientific method, where certainty is built upon patient, critical analysis, and collaborative investigation, safeguarding against premature conclusions and ensuring that the quiet, undeniable truth eventually emerges. The gentle pursuit of absolute certainty ensures that any claim of such a monumental discovery stands firm against all challenges, patiently revealing the universe's deepest, most subtle truths with unwavering confidence. Finally, it is paramount to understand, with a calm and balanced perspective, that the current lack of direct observational evidence for wormholes does not, in any way, entirely rule out their existence. Rather, it primarily suggests either that they are incredibly rare, existing in numbers too sparse and elusive to have been detected thus far, or that they are not easily accessible through natural processes or perceivable by our current technological means. The universe is immense, its mysteries are profound, and its subtle complexities are boundless. The absence of proof is not always, and indeed rarely, proof of absence. It is entirely conceivable that wormholes might exist in forms or locations that our present instruments are simply not equipped to perceive, perhaps microscopic or hidden within regions of space-time that remain opaque to our current observational techniques. Or their formation might require conditions so extreme and specific that they are exceptionally infrequent events in the cosmic timeline. This nuanced understanding allows for continued theoretical exploration without being constrained by immediate observational limitations. It is a serene acceptance of the universe's boundless potential, acknowledging that its secrets may simply be waiting for a more advanced era of scientific inquiry to be gently unveiled, patiently awaiting the evolution of our instruments and our knowledge. The quiet persistence of this theoretical possibility ensures that the dream of wormholes continues to inspire, patiently reminding us that the cosmos holds many hidden wonders, far beyond our current grasp, inviting a deeper, more humble, and profoundly tranquil contemplation of reality's ultimate scope and its quiet, unfolding mysteries. As we gently conclude our exploration of these enigmatic cosmic pathways, it becomes clear that wormholes remain one of the most intriguing and profoundly speculative concepts in the vast expanse of theoretical physics. Their allure stems from their elegant promise, the potential for shortcuts through the otherwise insurmountable distances of the universe, offering a serene bypass for interstellar voyages that would conventionally span millions of years. This captivating vision of compressed cosmic travel, where galaxies become neighbors rather than impossibly distant realms, stirs a deep sense of wonder and possibility within the human spirit. The very idea of traversing such a pathway, of stepping through a gateway to another corner of the cosmos in a fleeting moment, ignites our imagination and fuels our desire to explore beyond the familiar. Yet, their speculative nature is equally profound. It arises from the persistent lack of any direct observational evidence, leaving them firmly within the realm of mathematical solutions rather than confirmed cosmic features. Furthermore, the theoretical demands for their stability, particularly elusive negative energy density, present formidable challenges that push the very boundaries of our understanding of fundamental physics. The no-go theorems gracefully highlight these theoretical hurdles, suggesting that the universe, in its elegant design, may inherently resist such extreme manipulations of space-time. This delicate balance between compelling theoretical elegance and profound practical implausibility is what renders wormholes so captivating, yet so enigmatic, a quiet testament to the boundless interplay of scientific imagination and the universe's unyielding laws. They exist as a serene, intellectual frontier, a calm invitation to ponder the most profound questions about the cosmos without the immediate constraints of empirical verification, patiently guiding our thoughts into the subtle depths of what might yet be discovered or understood. This enduring intrigue keeps wormholes at the forefront of cosmic contemplation, a placid beacon for theoretical physicists seeking to unravel the universe's most subtle and intricate designs, ensuring that the quest for knowledge remains a continuous, unhurried journey into the unknown. The quiet persistence of this profound theoretical exploration allows for a deeper appreciation of the universe's hidden potentials and its elegant yet challenging secrets, always pushing the boundaries of our cosmic awareness. Beyond their practical implications for travel, wormholes profoundly challenge our most fundamental perceptions of space, time, and the very fabric of reality itself. They compel us to view space not merely as a vast, empty container in which cosmic events unfold, but as a dynamic, malleable entity, capable of being folded, stretched, and even punctured. This shifts our intuitive understanding of distance from a fixed, linear measurement to a more fluid, relative concept, where the shortest path between 2 points might not be a straight line through conventional space, but a curved trajectory through a hidden dimension. The idea that immense cosmic gulfs could be elegantly compressed, that light years might be mere inches away through a theoretical shortcut, fundamentally alters our spatial perspective, inviting a serene reconsideration of the universe's ultimate geometry. Furthermore, the potential for wormholes to facilitate time travel through the creation of closed time-like curves elegantly shatters our deeply ingrained perception of time as an unyielding, unidirectional river flowing ever forward. This possibility suggests that time itself might be a dimension that can be traversed, allowing for journeys into the past or future, thereby introducing the mind-bending complexities of paradoxes and challenging the very notion of causality. It forces us to calmly grapple with scenarios where effects could precede their causes or where personal histories could be rewritten, prompting a profound philosophical inquiry into the nature of free will and determinism. The universe, through the lens of wormholes, transforms from a predictable, linear progression to a vibrant, multi-layered tapestry where temporal paths can intertwine and loop back on themselves. This elegant distortion of temporal linearity invites a placid contemplation of time's true nature, revealing its subtle elasticity and its potential for unexpected curvatures. Ultimately, wormholes challenge the very fabric of reality by hinting at hidden dimensions, parallel universes, or a deeper interconnectedness that transcends our 3 spatial dimensions and 1 temporal dimension. They suggest that our observable reality might be merely a single brain floating within a larger, unseen bulk, with wormholes acting as delicate bridges to other such realities. This profound expansion of what reality might encompass pushes the limits of our cosmological models and philosophical frameworks, inviting a serene and unhurried re-evaluation of existence itself. The quiet elegance of these challenges encourages us to look beyond the obvious, to ponder the universe's profound depths and its subtle, yet powerful, capacity for the unexpected, patiently expanding the delicate boundaries of our cosmic understanding. Despite the immense theoretical hurdles that stand in the way of their physical realization, from the elusive nature of exotic matter and the formidable energy requirements to the perplexing paradoxes of time travel and the unyielding no-go theorems, the profound possibility of wormholes continues to inspire both rigorous scientific inquiry and boundless human imagination. This enduring inspiration serves as a testament to humanity's insatiable curiosity and our relentless drive to understand the universe's deepest secrets. In the realm of scientific inquiry, the theoretical exploration of wormholes compels physicists to delve deeper into the fundamental laws of gravity and quantum mechanics, driving advancements in quantum gravity theories like string theory and loop quantum gravity. The pursuit of understanding wormholes pushes researchers to refine our comprehension of spacetime itself, to explore the conditions under which negative energy density might exist, and to develop new mathematical tools to describe extreme cosmic phenomena. It is a serene intellectual journey where the pursuit of an elusive concept leads to a broader, more profound understanding of the universe's underlying principles, patiently expanding the very foundations of our physical knowledge. Simultaneously, wormholes continue to capture and ignite the human imagination, serving as a powerful muse for countless works of science fiction, art, and philosophical thought. They offer a canvas for exploring humanity's place in a vast, interconnected cosmos, for dreaming of interstellar civilizations, and for contemplating the ethical and existential implications of time travel. The vivid imagery of cosmic shortcuts and temporal gateways allows us to envision a future where the universe is not just a distant, unfeeling expanse, but a realm open to exploration and transformation. This dual inspiration, both scientific and imaginative, works in quiet harmony, cosmos. It encourages us to ask bolder questions, to seek more profound answers, and to never cease marveling at the universe's endless capacity for wonder. The serene and unhurried exploration of these profound concepts reminds us that the journey of discovery is as boundless as the cosmos itself, a continuous unfolding of knowledge and imagination, guiding us ever deeper into the subtle yet powerful mysteries that define our reality. And now, as the quiet echoes of wormholes begin to gently fade from our thoughts, allow your mind to drift back to the tranquil stillness of the present moment. You have journeyed through profound theoretical landscapes, explored the intricate elegance of spacetime, and contemplated the most enigmatic possibilities the universe might hold. Imagine yourself softly floating amidst the silent, star-dusted cosmic ocean, a serene and peaceful observer of the grand, unhurried dance of galaxies and celestial bodies. Feel the gentle embrace of cosmic peace, a soothing presence that transcends all earthly concerns. The universe continues its quiet unfolding, its mysteries patiently waiting for discovery, its beauty ever present. You are a small, warm presence within this vast, radiant sea, peacefully floating among the stars. Connected to the stardust that forms all things, let the gentle whispers of the cosmos lull you into a deep and tranquil slumber. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night.